Yeah, since we have a full schedule, let's get started. It's my pleasure to introduce our first speaker, Caslav Brukner, who is a group leader here at IQOQI and also deputy director, I think. Please clip this somewhere to your judgment. Cool. Should be fine.
Should be fine?
Yeah, I think so.
All right. Okay. So, good morning, good afternoon, good evening, wherever you are. It's a great pleasure to welcome you here from Vienna, from the Institute for Quantum Optics and Quantum Information. I hope you will have a pleasurable day. There will be a lot of talks, mixed, more senior and younger researchers. And when I was invited to give this opening talk, I was thinking, what will be this common, maybe one theme or subject that is intersection of many, if not all, research groups at IQOQI Vienna. And that was a quantum reference frames. And I decided then to give the kind of overview talk with second half a little bit of a new things, and to justify why this interest in this topic is in IQOQI Vienna. So why quantum reference frames is the title of my talk. So I think the reason for that is that we have a good understanding, or that our physical theories do not pre-assume any external third point view on physics. And neither our theories nor our observations thus far prefer any external reference frame. There is no meaning in the position in space-time a priori. There is no meaning in the orientation, the space a priori. And without external reference frame, then all our physical statements must be relational. So if you have two systems, S1 and S2, you want to say something about their relation, like a relative distance, perhaps between 2-point particles. So that brings me to probably the most important slide in my talk. If there are no external reference frames, then I'm free to choose one of the systems as my reference frame, with which respect I can describe other systems. However, the belief is that the physical content of my statements will be not changed by the choosing different reference frames. So what I mean with this are probabilities for relational observers are invariant under this choice. However, my description of physical situation may change. The states, the Hamiltonians, the measurements can be represented by different operators. You can think about that as, for example, that any statement about the spin in a Stern-Gerlach experiment about the probabilities to obtain spin up is given by the relational angle, so to say, between the preparation and measurement device without really taking into account what I choose to be the z-axis in my laboratory. So here is another example, and it's within the classical reference frame. Consider this B system. I don't know whether there is a laser actually here. I have to turn it upside down. No, sorry. So I have to point on the screen, or how?
No, you think you can point with the laser?
With the, okay, now I see. Okay, good. So let's think about the classical reference frames, and let's think about B being a composite system, many, even the rest of the universe if you want, for which you believe that there is a translation invariant physics of all these system speed. Then this translation invariant physics doesn't depend on me choosing now one of the maybe heavy classical reference frames, a wall of my laboratory, as the origin from which I will define maybe relative distance and absolute distance to A, but of course from an outside relative distance. And so the only thing which might change by changing from, for example, C to A reference frame is that I will apply some unitary on the state of the system beeps. But when I want to measure something, I will need to do this also for the operators that represent my measurements, such that probabilities are invariant. So the idea of the quantum reference frames is very conservative. It just tells, okay, but your wall, no, maybe it's not always wall. Maybe you will sometimes use a lighter particles. And even if you use a wall, after all obeys quantum mechanical laws. So one should be prepared to a weakening of a picture from above, in a sense that I can think about reference frame being in a quantum states, being maybe in superposition state, or even being entangled with some other systems, in such a way that I can have some framework to jump from my initial reference frame to a new reference frame. And this is the working horse in all these cases when we deal with so-called ideal reference frame. I will go back once more to this notion, namely that when I choose to change from A to C reference frame, I have to make some kind of a controlled unitary on the reference frame and apply my group of transformation on my systems B. Now, interestingly, I say this is a conservative view because you can go back and you can think about really ideal reference frames, meaning that group element is are orthogonal to each other, and they are also very localized systems. And everything what I said and what was maybe more easy to accept applies again in this classical limit, if you want. Now I'm coming back to the actual questions that I want to address now, after this short introduction. Why quantum reference frames? I see 4 reasons for that. As in ordinary physics and ordinary classical reference frames, we tend to choose such reference frame in which physics seems simpler. There is nothing very deep about that, but it's a very useful tool to compute things. So some quantum reference rates are better than the other, although they are all democratically equal. Then the second reason is, well, you can guess right dynamics in untested regimes if you do assume that your physical laws are invariant under quantum reference frames. You can also maybe find observables that are invariant under quantum reference frames and have been not noticed so far as interesting when you were considering invariance under classical reference frames. And finally, you might hope that there is something new and interesting coming out of that. Okay, so let me go one by one. Here's an example that I sometimes tell in the discussions after the conferences is historical example. People were troubled to understand how atmospheric muon can reach Earth. Because if you look at the decay rate or of the muons, it's too short for the distance to reach Earth from the atmosphere. And of course, the solution to that, when the people thought about that, was invariance on the Lorentz transformation, or that physical content should not depend on which Lorentz frame we choose. So we can easily go into the muon rest frame. And the muon rest frame, this decay, time of decay, is in the rest frame. And in the muon rest frame, it's the Earth which is moving towards the muon with a velocity, let's say, minus v. And therefore, the muon, what sees as a distance is a Lorentz contraction of 660 meters. And that's why, from the muon's point of view, you can reach the Earth. But of course, we do this just in our thoughts. We don't need to move ourselves physically in this reference frame. And then we go back into the Earth reference frame, in which the muon is moving towards us. And then we, out of these considerations, and the fact that the muon has decayed, so it's the same decay, but different reference frame, can infer what will be the time dilation on the Earth that will be exactly such that muon can reach us. So all this exercise was actually not very active moving into another reference frame, but also in our thoughts we have done this. And this is some indirect proof that actually physics really doesn't depend on our Lorentz frame. Now the question that I like always to pose myself when we talk about quantum reference frames is, what if the muon is moving in a superposition of velocities? And the story is the same. And the story is the same. What you can think here is that you start again from the rest frame. This is the frame in which you can define this decay rate and time for the decay. And then you think the rest is moving in superposition towards to the muon. In particular, the Earth, then there is environment here, and some particle contact of a muon, one muon. And now the muon decay will be some interaction between the muon and the environment, seeing the decay of the muon into environment. And once you define this after some time, you can go back into the Earth reference frame, trace out the environment, and get the situation which we expect, namely that depending on velocity, the length that will be traveled by the muon will be in a classical mixture depending on the velocity, because the time dilation will be also in the classical mixture after we trace out the Earth. So this is an exercise. These papers are not about the muon, but the very similar situation appears in entanglement between spin and momentum. Okay, so that's an example that for a first case where it is useful. Some quantum reference frames are simply better, easier to understand than the others. Well, next one, and I will just be very superficial on these points until the last one, we can guess the right dynamics in non-tested regimes, for example, in the regime of a quantum gravity. And here is something which many of you are familiar with. You can ask yourself a question: what is the nature of the gravitational field which is sourced by the mass in a superposition? And even if you do not take any point on that a priori, but accept that physics is unchanging by changing from one reference frame to another, you can think about that you can go into the reference frame of the large mass in which the rest is in a superposition. This is a problem that we know how to solve because the metric is fixed, and to whatever level of exactness you can do these things. You will, for example, in some semi-classical regime, see that the system S then moves in a superposition of geodesics toward the mass, and then you can go backwards in the first reference frame and get your answer. Of course, for that to be true, you have to assume that the physics doesn't change, that the probabilities, that the fact that they will collide together, the system, and or move towards each other and Earth doesn't depend on which quantum reference frames we choose. But this has a very important consequences as a possible way to distinguish different approaches to quantum gravity. The reason for that is that in semi-classical gravity and in collapse models are models which are not invariant under this change of quantum reference frames. And the reason how you can easily see this, look the lower picture as a reference frame of the large mass and the upper picture as a reference frame of the small mass. Now in semi-classical gravity, the gravitational field is sourced by the average of gravitational field. So if I put a small mass in a superposition, then this superposition will be such that the small mass will move towards, no matter where it is, towards the large mass. From the point of view of the reference frame of the small mass is exactly in the middle of the two amplitudes of the large mass, and therefore the average gravitational field is 0, and it will stay there. Therefore, these two pictures gives different answers. On another way, semi-classical gravity is not invariant under the quantum reference frame. The same is the collapse model. In the collapse model, the collapse happens only if you have a large mass in a superposition, or the time for collapse is very short for that. So if I have a localized large mass, I will have a very long survival of this superposition. But when I go into the reference frame of a small mass, it will be collapsing, and therefore 1/2 probability will have one or the other collapse, making these two situations not equivalent. And finally, you can think about any linear quantum gravity or anything which obey linearity of quantum theory, and these two pictures will be the same, and you will not have any difference in both reference frame. The two will go and move towards each other. And now I want to move to the interesting topic, and this I will be also very superficial. of finding observables that are invariant on the quantum reference frames, because this is a kind of a new thing coming up. Obviously, all observables that are invariant on the classical reference frame will be also invariant on the quantum reference frame. So what you can hope for is a little bit of something new coming that you overlooked as important thing. And methodologically, it goes in the following way. Already from this picture, and I didn't say this, but many people are already aware of that by changing from one quantum reference to another, what you change is the tensor factorization of our tensor product factorization of the Hilbert space. And then it's not surprised that what changes is also superposition and entanglement, because what was the system in one reference frame is not anymore the system in the other reference frame. And therefore, by moving from a classical to quantum reference frame, you weaken something. Entanglement and coherence are invariant on the classical reference frame. Once you move to the quantum reference frame, they are not anymore. However, you can find a new quantity, and this turns out in this work to be the sum of the coherence entanglement, which is again invariant on the quantum reference frame. And in this particular case, the measure of entanglement was entanglement entropy and relative entropy of coherence that in the sum give a constant. Here's another example. The fact that, and methodologically is very similar. When you move from, so when we define the events, we can think about events being events in superposition or events which are localized. And when you change from one quantum classical reference frame to another reference frame, the localization, the fact that whether the event is localized or delocalized, do not change with itself. However, when we move from classical to quantum reference frame, the localization of the events can change. So something which was local maybe will be dislocal or delocalized and the other way around. And then you can ask yourself, okay, if the space-time localization of events can change, is also the causal order changed? And this is what was proven in this work, that the causal order is nevertheless invariant on the quantum reference frames, even where the localization of events may change. And the way to see this is that in one coordination of so-called quantum switch, and I have no time to go into this, you see that maybe A is delocalized and B is localized. And the causal order is such that you have a superposition of either A being before B or B before A. And this is coordination in the green field, quantum coordinate field. However, if you go in the gray one, you may change the localization. So it's not anymore that A is delocalized, it's B that is deslocalized, and A becomes localized. And again, I have a superposition of two trajectories, or two causal orders, B before A or A before B. The localization of individual events has changed, but the causal order did not. And that's indefiniteness as a measure of whether it's definite or indefinite. The causal order is invariant on the quantum reference frames. How much time do I have?
You have 15 minutes left.
15?
Yes.
Very good. Good. Now I can go to the, well, the thing that I'm particularly excited about, and it's a recent work, and it goes beyond the previous example. The previous examples were weakening of our classical reference frame in a sense that we can think about classical reference frame being in some kind of superposition of semi-classical states. And if I can make some order about that, you can think about the left-hand side as a classical case in which I have idealization of the reference frame in the sense that they are orthogonal to each other, sharp, but they're also localized in the parameter space of this representation of the group. And then we talk about many examples in the previous slides in which we weaken that and we think about superposition of these semi-classical states. But actually going this way further, thinking about that you can never have infinite resources in your laboratories to make your representations sharp enough, you have to think about overlapping states of the reference frame. and with those for which we don't have a sharp distinction. Okay, so here is the work which we are doing now with Esteban, Nathan, and Luis, and concerns about the most radical departure, I would say, from what I described so far in our framework, how we deal with quantum reference frames and quantum systems. It starts with a question about that every experimentalist in the lab test and verify when they want to verify quantum mechanics, and this is how often does a given outcome occur in n runs of experiments. So you can get your favorite outcome here and ask yourself how often this outcome happens. And one way to quantify this is through relative frequency operator. Relative frequency operator is for any given P of EM and a repetition of my experiment n times. I will just count in the system of n identically prepared systems how often this P of EM happen. And in a finite number of trials, this will happen k times if you want. Okay? Now, here is an interesting, actually, theorem that connects the relative frequency operator with the Born rule, how we compute them in textbooks. And it's given by Finkelstein, Hartmann, Herwood. It tells the following story. Given an n-copy state, so this is this IID when all n copies are in the same state, and a P of EM element E, the mean value of the frequency operator is exactly given by the Born rule. And the variance of the frequency operator vanishes in the limit of infinitely large n. So in certain sense, you can think that this IID state is an eigenstate of the frequency operator when the number of trials goes in ideal case of infinity. And so in the experiment, what you will do, you may have n trials, and you will get some relative frequency that will start to oscillate or not converge for a while, going down with 1 over square root of n, according to the law of large numbers, and then going towards the Born rule computed probability. So one could say this is the theory which gives us, these are our empirical relative frequency, but they tend towards to Born probability. Now, when we want to describe this situation, and the reason we have this stability of the probabilities, at least in this limit of very large number of repetitions, is that our apparatus in the laboratories are very heavy. They allow us, there is no back reaction from the measurement to our reference frames, and we can prepare the experiment under the same conditions. This under the same conditions is a hidden assumption when we talk about IID, namely identically prepared independent systems. So we have to ensure that every time we measure another copy of the system, our laboratory has not changed, our reference frame has not changed. Now we want to go into the finite or non-ideal reference frame. And this already indicates that this will not be the case. But first we have to then understand what we actually measure in absence of external reference frame for group G. We measure something which we call relational relative frequency operator, which is for the people familiar with quantum reference frame, G twirled for the group G of the reference frame and the frequency operator. So what you see here is this sum, which you recognize from the previous slide about all n systems of your P of EN, but now this is G twirled. Okay, and then here is the interesting result. Well, if you do so, in the limit of infinitely many repetitions and for non-ideal quantum reference frames, the relational relative frequencies for a pair of measurements may not commute anymore. So even if I repeat n times my experiment, by measuring two P of EMs, this commutator may not be 0. It is actually equal, not the commutator, but absolute value, the norm of this operator evaluated by IID state, is given by the norm of the commutator that acts on the reference frame and applied on one system. So whether this commute or not depends on your reference frames. They do commute, however, in two extreme cases. First is ideal reference frames. We are back into the previous theorem. Or if you don't have one reference frame for n copies, but you have for each copy each reference frame, which is basically, again, IID system, because then each system has a reference frame. The composite system is one system, and they are equally, identically prepared. But we will not be interested in A and B. So what this gives as a consequence is that you do not have any more convergence of the relative frequencies, in a sense that they do not converge to the same value. They converge to some value, but by repeating this n times and letting n go even to infinity, they may converge into the different values. So you have some uncertainty in distribution of relative frequencies as compared to non-existent uncertainties to the convergence to the same point in the case of infinite resources and ideal reference frames. So even in the limit of infinitely many repetitions, the distribution of relative frequency does not become sharp. There is a residual non-zero standard deviations that goes a little bit down with square root of n, but then saturates and then and doesn't go to the zero. Now, with every such a uncertainty in a physical observables, we may ask ourselves, is this just our classical ignorance? Maybe I can still think about my experiment as having classical mixture of IID situations, that somebody is schooling our source, so let measure n times, then I change the source and n times and so on, such that this is just a apparent thing. And people who are familiar with the Finetti theorem will say maybe this is just a situation of a de Finetti problem in which you have a classical mixture of quantum states that will give this distribution. And the answer is no. And the reason why we say it's no is that by measuring these relative frequencies, you can violate Bell inequalities. And in that sense, we can prove that the joint probability for measuring relative frequency on Alice and Bob side with one pair of reference frame and n pairs of particles, and then repeating this procedure many times, cannot be written in a locally causal fashion, meaning that the probabilities of probabilities, or however you want to call them, cannot be understood as an ignorance about some underlying, well-defined, born quantum probabilities. And that's a very important message. So I want to conclude with one slide about how I see this development. And no doubt in the historical development of physics, we are getting into deeper and more fundamental understanding of our physical world. But at the same time, the measure how we make predictions in these theories is actually declining. Because with the Newtonian mechanics, we have a full a maximal predictability in a sense that the theory was deterministic. With the statistical mechanics and also thermodynamics and also gambling, we understood that we have to introduce the probabilities, but these probabilities always have been understood as ignorance about maybe even deterministic account of the events. Once the quantum probabilities came into the play, I guess the initial reaction was that this is just another way of probabilities of the same kind, but the Bell's theorem and Kochen-Speck's theorem put some warning on that and say maybe this is not the way, maybe these probabilities are objective in a sense of non-reducible on any deterministic account. And in that sense, these are the probabilities of individual outcomes. But nevertheless, quantum theory says there is something which is definite, and these are the probabilities for all possible measurements. They are well defined, so you can rely on them. And this is another like high order of the same game. There are situations in the presence of non-ideal frames when even that can be put in challenge and say that these probabilities of probabilities, or the probabilities of relative frequencies in the limit of n goes to infinity, are again subject of Bell's theorem, and therefore might not be understood as ignorance of our underlying well-defined Born probabilities. And with thank to all my collaborators and to my group, I would like to end this presentation. Thank you.
Okay, thank you, Caslav. I think we have time for one quick question. Ofek, your hand was first, so. Please, in the mic.
Thank you, Caslav. This was very interesting. I wanted to ask if the last part with the probabilities of probabilities, do you see it as an experimental signature of the covariance of the laws to reference frames? Is this one thing you have in mind? That if this is really the case, if you see in experiments that the probabilities have those standard deviation, then it means that all of the calculation was correct, and then in every reference frame, in every non-ideal reference frame, as they are in nature, you will be able to compute the same frequencies.
Good. That's a very good question. So what is the what is the relation of the first part of the talk with the second part of the talk? And can we preserve the physics the same even when we move from one non-ideal reference frame to another reference frame? I did not think about very deeply, but my immediate answer would be that that the statement about how strongly relative frequency fluctuate is given by the strength of the reference frame. And therefore, if the merit is really the probability distribution of relative frequency being the same when we change from one reference frame to another, I would suspect that if you change from one non-ideal reference frame to another, but of the same size, meaning the overlap between the states is the same, then I would see this as invariance. There is maybe a weaker way that there will be some, even independently of the size of the reference frame, there will be some distribution relative frequency coming back to the extreme case when you have ideal reference frames and shrinking the standard deviation to 0.
Okay,
thank you.
Let's thank Caslav again. The mic. So, it is again my pleasure to introduce our next speaker, Veronika Baumann, who is a postdoctoral researcher at IQOQI and also at the Technical University of Vienna.
Okay, great. Okay, thank you for the introduction. And I'm going to talk about time delocalization and causality across temporal quantum reference frames, which this doesn't do it. Okay, then I do it like no, it does. Is joint work with Max Locke from the TU Vienna. This is the paper. This is the QR code of the paper, in case you want to read it. No. Okay, let me start with a few words on causality. So, as we all know, in order to talk about causality, you need a notion of correlation between events and a notion of an intervention, so that I can distinguish mere correlations from causal influences. In the foundations community, there are two notions of causality lying around. One, the more established and older one, I would argue, is space-time causality. So where my events are points in space-time, and the light cone structure determines how they can causally influence each other. So if I have an event A here, I draw this thing, and then I can say that A can causally influence B, but not C, for example. Okay, there is another notion, which I would call operational causality, which comes from the quantum info side of things, where we talk about causal relation in terms of signaling correlations between quantum operations. So if my events are now basically the application of an operation. And if, for example, A causally influences B, like here, I draw an arrow there, which just means I have signaling probabilities between them, between the two operations. And if C causally influences B, then I draw an arrow here as well. Okay, so I come from this side. So for me, this is way more natural to think about. However, these two things, while they both capture some ideas we have about causality, are distinct things. And to me personally, it is not entirely clear how to best relate them. So just based on this, I would like to know how to bring this, which I know better, over there. And what I'm trying to do, therefore, or in this research project try to do, is to think about operational causality in a way that is at least better suited to talk about space-time causality as well. And I'm trying to do this by phrasing operational causality in terms of relational quantum dynamics, which, thank God for the sake of fitting in with the crowd here, will be related to quantum reference frames. Okay, let me briefly talk about operational causality. As I've already mentioned, I'm interested in signaling correlations between quantum operations. So I have quantum operations, which are sets of CP maps that might produce or will produce in general some outcome. And the application of this operation constitutes the event for the sake of causality. Then I usually look at something like this. So I have a general evolution, and at some point I apply an operation to this subsystem, and at a later point apply another operation, which for the sake of simplicity I now consider to be just an observable, to another subsystem, and then I look at the probabilities of these two. And if I then find that basically my probabilities for the outcome B here depend on which operation I applied here to A, I have signaling from A to B, and that means in the operational causality framework that A causally influences B. Okay, now relational dynamics. In relational dynamics, I consider a joint Hilbert space of a system and what I will call a clock, and then say that the physical states I'm interested in satisfy a Wheeler-de Witt-like constraint equation, which means that if the constraint looks like this, I have a part that acts only on the clock, one on the system, and potentially interaction terms. Then I can, based on this clock Hamiltonian, define time states and expand my solution like this. And then the system states, if I condition them on some clock time t, I find that they evolve in the case of an ideal clock without any interactions. I can show that this evolution is the actually regular Schrödinger evolution. And in that sense, I have relational dynamics. So this thing here, which is the solution to the constraint equation, doesn't evolve, but these here, the conditional system states, do evolve in time. Time is well shown by this clock. Suggestive picture to illustrate this. As I said, I have my static solutions, and I can run through clock times here. And if I look at a specific time, it's like looking at a slice in this block here, and then I have the conditional system states. And then I just run through here and see that this evolves. And in that sense, this clock and these time states are basically my quantum version of a parameter time or a time coordinate. And in that sense, they are what we call temporal quantum reference frames. Okay, now that I've called them such, I should probably think about how to do reference framey things with quantum reference frames. And for that, I look at multiple clocks. So I have my original system, but now different potential clock systems. Then I can do what I just said for each clock individually. So I, again, have defined time states and can expand my solutions to the constraint equation like this. Okay, now I go to big picture stuff. So in general, a general state on this Hilbert space is what I call a kinematical state. And then if I solve the constraint equation, I basically project onto these states here, the double cats one, and I can call this the physical Hilbert space, which consists only of the solutions to the constraint equation. And if I now want to look at the conditional states with respect to a certain reference frame, I just project on this clock. Then I get, for example, here, Hilbert space with respect to Ci, and I can do the same if I expand it according to the other clock here. That is nice because this beautiful picture now tells me what I need to do in order to change temporal reference frame. Namely this, I basically go back here to the physical Hilbert space and then just go down there again. Nice, so I can do everything I would want from reference frames, also for temporal ones. Okay. Now let's bring operational causality back and think, how do I do this? Okay, if we start with an ideal clock, a single one, it's pretty easy because I can basically look at any evolution I want and just add this clock that doesn't interact with anything and therefore implement this evolution in relational dynamics. So I look at the unitary purification of whichever evolution I want to have. Need to do some ancillas here, add the clock, and then if I trace out the ancillas, I have the general evolution I care about. Okay, but now, if I really want to do the causality investigations, I need my interventions. So what do I do about the interventions? Well, there are two things I could do. At first, I could think, okay, what should be an intervention? If I apply an operation on the system at a time t2, I might want to look at something like this, right? Looks great. Doesn't work, unfortunately, because if I apply this to a physical state, like a solution to the constraint equation, I end up in something like with something that is no longer a solution. So if we go back to a picture, just one clock here now, I start here, apply my supposed intervention, but then I end up back here. Okay, so that's not how I do it. Okay, then forget about this. Let's look here, because there we know what we're doing. At a certain time t, we just apply the operation we care about, right? And if I now want to go back here and like see what this looks like, I just apply the inverse of this map. Okay, then I suggestively insert an identity here, and then I can see that I have this here, which is a solution to the constraint equation, and then this thing here, which is different from this, but is basically now a physical observable or physical operation. So something that I can apply to a physical state, which leaves me in this Hilbert space, but captures the notion of an of this operation at this time. And if I now want to talk about causality, I need to consider different interventions, of course. And from this form, I can immediately read off that basically different interventions now correspond, well, to different MSs here, and therefore different solutions to a single constraint equation. So I have the same constraint operator, and then I add different MPhys here. Okay. There is another way of doing interventions, though, and that is incorporating them into the constraint operator by well-chosen interaction terms, namely things that look like that. So I have my free Hamiltonian of the clock, free Hamiltonian of the system, and then I write down something like this, where t is defined by the time states, and k is so chosen such that e to the I ks is a purification of the operation I want to apply. So I again need 1,000 ancillas, but I can add them. And if I do this now, so if I want to consider different interventions now, I need to modify the constraint here, right? So another intervention means I put another k operator here. That means different interventions are now solutions to different constraints equations. However, I can group them into like equivalence classes if you want, where everything else stays the same, but I only vary the intervention I want to consider. Yeah, so if I want to write this out more nicely, so the psi m's, so solutions that only differ in m, now correspond to different constraints. Okay, great. If I do this with everything I've said so far, perfect. I can do my operational causality in relational dynamics. If I want to choose interventions model 1 or 2, doesn't matter. I get the same. Everything works out. That would be a very short talk, though. So
they're provably equivalent, the two ways of doing it. You can always find the...
For ideal clocks, yes. They give the same probabilities for everything you could consider here. For non-ideal ones, not. Esteban has a paper on this with Ladina. There is a difference, but yeah, that is. Let's stay with ideal clocks. I mean, there will be a difference now, even for ideal clocks, namely if I consider multiple clocks. The interventions model 1 will basically fail for the purpose of talking about causal relations if I consider multiple clocks. Why? Well, okay. Simplest example, I have 2 subsystems and 2 reference frames. Okay, so now I do my interventions model 1 and apply something like this. So A and B here. If I change reference frame now, however, I end up with something like this, because of what Caslav mentioned in his talk as well, that the subsystem structure is not preserved under change of quantum reference frame. That also holds for the temporal ones. And I mean, this might not look bad in general, because most of all, because the probabilities stay the same. They are, of course, invariant under change of reference frames. But I get trouble when I want to talk about causality now, right? Because if let's say I find signaling, so I can detect whether different applications of different operations here in the outcomes of B. But what would I say in each reference frame? Well, here I can say, yeah, this is clearly due to a causal influence from A to B. But here I cannot say anything like that. It gets even worse if I want to think about hypothetical agents who apply these operations. So let's say A does this and B, like Alice applies this operation, B applies this one. And then also I give the different clocks to the different agents. So Alice is basically associated with C1 and Bob with C2. Yeah, well, then I get this thing here, and nobody can say anything about causal influences anymore, because the other operation, like that is applied by the other agent, always appears delocalized and acting on all the subsystems. Well, that's kind of bad. Good news is we have interventions model 2, and that one is fine. So if I now have something like this, so the operations are basically timed by clock, so they are connected here. Because this thing is now a part of the constraint, which subsystem it acts on is not changed if I go to a different reference frame. What, however, does appear, this is a general feature of multiple temporal frames, is something like this. I have some delocalization in time, because I cannot perfectly synchronize these 2 clocks in some sense that we make precise in the paper. But if I choose this all carefully, so basically wait enough to have my outcomes here, and the time delocalization is not too bad, I can do everything I want and talk about operational causality here in this version of relational dynamics and in this version of modeling interventions. In general, operations always appear time delocalized in any frame of clocks that do not time the intervention. So since here this intervention is timed by C1, here they appear at a sharp time of application, or I can set it up such, but they necessarily appear time delocalized in the other, right? And if I do again the thing with associating different temporal frames with different agents, therefore let them time differently, I have some delocalization in every frame. But this can, first of all, I can set it up that it works out nicely. Second of all, this is a feature, not a bug, because it allows me to do the following: indefinite causal order. So, simplest example, I look at something like this. So I have the 2 clocks, the system, and now one operation timed by one clock, the other operation timed by the other clock. If I choose a suitable, well, kinematical state, I have no time to go into the details here, but I can set things up such that solutions of the constraint equation have a time delocalization across the one well-timed intervention in both frames. So this sounds worse than it is. The picture that goes along with it is this. So this is in the frame of C1. The operation here is applied at a certain time, but in the operation of the other frame looks like this, and this is in a temporal superposition of being applied before A and after A, which if you, well, either if you're familiar with it, you might recognize, or if you have paid very close attention to Caslav's talk, you will recognize this as the evolution of the quantum switch, which has been known to be in some sorts implementable and compatible with relational dynamics before. We have now just said showed in an overview and systematic way how and why exactly. And with that, I say thank you.
We have time for one short question. Anyone like?
Everything clear. Sorry.
So you started the talk by motivating the difference between the space-time notion of causality and the more operational one,
Yes.
right? So how do they fit together within this formulas of the different clocks that you're presenting here, if you will? Is there a good way of seeing the connection between the two?
Well, it's better than with them not being there, right? So that's one thing. I'm not claiming that this now fully establishes the bridge, but you can at least write down relational dynamics like this constraint equation in a form that are way closer to actual relativistic picture, right, where you have space-time coordinates represented in that way, which is not what we did in the paper, but this is sort of at least a version of quantum theory that lends itself to be translated into relativity. In that sense, we are getting closer to that. And it already hints, I mean, this is not in the paper yet, this has been ongoing work forever, but it already hints at something, well, where you can think of that maybe the space-time causality, notion of causality will limit some of the stuff that you could do in this purely information theoretic version of causality, because it looks as if some very weird processes, like notions of indefinite causal order, do not have a meaningful counterpart in the relational dynamics version already, or you have to go to something really, really extreme, which would be sort of an indication as to why we, well, not only have not observed them, but also wouldn't know how we could. Yeah, so that's the bridge, I would say.
Okay, then let us thank Veronika again. Okay, our next speaker is Jan Głowacki, who is a postdoctoral researcher in the group of Markus Müller here at IQOQI. Please, Jan.
Okay. Hello, everyone. Since this is a very, very short talk, this gives me an opportunity to present a very overview of the framework that I'm working on, which actually I always wanted to do, especially now since we've made some progress on the maths side of the whole thing. So let me go straight to the maths then. The general idea of this research is to try to look for ways to express these ideas of relationality in operational ways inside of the framework of operational quantum physics developed by Paul Bush and others some years ago. So we were using the established mathematics to try to express these intuitions. So yes, and the idea that I came up with recently is that the core object in this whole endeavor is actually a mathematical tool that allows you to integrate operator-valued functions with respect to operator-valued measures. And I'm going to try to give you a short argument why this is the case and where it leads us structurally. So the setup is as follows. So we're considering systems that are being modeled as W-star algebras. You can just think about them as algebras of operators on a Hilbert space. And we go beyond now this paradigm where systems are just put together with a tensor product. it turns out to be enough that they commute inside of a bigger environment that is to be thought of as like quantum field theory, or just a world in which these two systems that we choose to describe relative to each other live. And on top of this, we introduce an observable, so a POVM that is based on some space. That's a measurable space. So these are like minimal requirements for this theory to take off. Okay. And then the idea is that whatever we're going to measure on the system S is going to depend on the configuration of the reference system, which is itself given in terms of a quantum observable. So we have a POVM on a space sigma, and we have an observable that depends on points on space sigma. And we use this integration theory to average out this whole setup and give rise, arguably, to observables that live in this bigger algebra and are relational. There is something relational about them. So that would be the starting point. And the key idea is that we are trying to describe observables in quantum theory that are defined relative to measurement setups. And these measurement setups will include some sort of a reference system and an observable that describes its configuration. So this is very abstract. And I would love to take your questions now, but there's no time for that. I'm just going to go on and see maybe there's going to be something intriguing happening. So what this has to do with quantum reference frames, well, I think actually quite a lot. So the next step is to put some symmetry extraction on top of this setup. So we're going to have a group that's going to be represented on all the objects that I introduced. So it's a topological group, and it acts on this big algebra in a way that it restricts to action on MS and MR independently. And it also acts, importantly, on this sample space of our observable. And then when we have such a setup, there is various kinds of requirements of consistency that we could require. So first, we could say that these functions functions of operators on the system that we consider, they need to translate equivariantly with respect to the group action. So on the left side, it's a group action on the set sigma. On the right side is this representation. Another condition is to ask the POVM to be covariant. And another one is to ask for the operators that arise out of this integration procedure to be invariant. So this is, I think, aligned, at least conceptually, with what Caslav was saying about the need of covariance on the level of systems and then invariance on the level of relational observables. So it turns out that these three conditions, they're very much related. In some setups, any pair of those implies the third one. But what is completely always true is that the first two imply the third one. So if I restrict to observables that are equivariant, and I assume my observables, which I'm now going to call frame observables, when they are covariant, so if I have these two conditions, then always the integration procedure is going to give rise to invariant observables. And that's the main point of this story, to develop these invariant observables in as much generality as possible, because as you can see, this group here is just a topological group. So it can be applied in principle very, very broadly. So this is how we define now the relativization map. So it's going to take equivariant functions into invariant operators. And so conceptually speaking, it's just a restriction of this very general integration procedure to the setup where there is also group symmetries involved. And well, mathematically speaking, this also seems like a very structural result in theory of W-star algebras. It's just like this space turns out to be a W-star algebra itself, and it's all very nice. So we can ask me about this later. And how it relates, because well, I guess some of you, well, you heard me speaking a lot. So you've seen Yen defined differently. So normally the domain of this relativization map is the algebra of operators on the system, or some invariant subalgebra. So this is compatible in the case where the action of the group on the space sigma is transitive. We have these two cases. Either sigma is just homeomorphic to the group, And then the space of equivariant functions is actually the same as the algebra because every such function is determined by a single value because of the covariance condition. And a similar thing happens if the action is transitive but not free, then we have a homogeneous space, and the relevant domain is the space of operators invariant under the stabilizer. Okay. I know it's too fast, but well, that's the picture I have in mind. And then I'm gonna say a little bit, like back to the title of my talk. What's the geometry that goes in here? And it goes because part of the setup is this action of the group on this topological, on this space that can be a topological space. And from this perspective, like because the framework is now developed for like arbitrary actions, we can distinguish these two cases that I just described, when the action is transitive and free or not free, but we can also push it further, and this is what I find really interesting to investigate right now, because when we drop this transitivity requirement, we can also investigate setups where the symmetry structure is a principal bundle, which opens up the whole area of like trying to apply this operational approach to quantum reference frames to gauge theories. And there's even like more general cases, but let's not talk about everything. The main message for this is that by considering very general actions on these sample spaces of our frame observables, we can now cover more general physical models and try to construct alternative models for, well, quantum gauge theories, for example. So this is work in progress, obviously, but yeah, now it seems feasible to do this rigorously within this framework. So that's the last slide. I'm just going to show you very briefly what happens if you take a look at this principal bundle case. So we have a space-time manifold, and the principal bundle, so like locally, it's just a Cartesian product of the space-time subsets in the group. And now the relativization map takes equivariant fields defined on the bundle. And actually, we now, again, have this bijection. So because of the equivariance condition, locally, you can think about these fields as actually defined on space-time, like in quantum field theory, and not on the bundle. And the relativization does this. So you can construct operators that are invariant with respect to the structure group, whatever that is. But what is even more interesting, I think, is that there is a natural notion of relational gauge invariance that appears here. So gauge transformations are endomorphisms of this principal bundle, and they can act both on the fields, like they normally do, but also because this frame observables are measures, you have this push forward procedure, and it turns out that if you do both, you just end up with not changing anything. And it is both trivial and I think really deep as a result, because it means that gauge invariance is really something that is built into this framework. You don't need to do any more averaging or integration or anything else. If you treat your frames as quantum in this sense, there is a lot of things. I mean, you have to do a lot of work at first, establish all these maths, but then you can just enjoy the results. Okay, do I have one more minute or not really? Okay, so just a couple of reasons why I find this interesting, and maybe some of you is going to find it intriguing as well. So what I talked about is that in this, with the tools of operator value integration, we can describe relational observables. We can then impose symmetry constraints, which allow us to construct observables that are invariant. And to do this, we need to have action on the sample spaces, which provides a structural link between this operational quantum physics and the differential geometry. So really, like, introducing extra structure on the sample spaces is, I think, conceptually the main insight of all this work. And this is the reason why it gives you this intriguing relations between all these theories. And because we have freedom for choosing all these different symmetry structures, the applications of the framework, they range across fields. And relational gauge invariance is something that is natively part of the framework. And yeah, we hopefully are going to get somewhere with this quantum gauge theory stuff. Thank you.
Any quick questions? If not, then I would.
Hi, Jan. We talked about this, but it seems that a very important thing is this Yen map. Is it unique, or how can you motivate it from some sort of operational ideas that under certain assumptions, this is basically your only option? Or
Yes. The answer is yes. So when the well, you need to put some assumptions, but to make it simple, assume that this sigma space is just the group itself, and that it's compact. And so you want to construct observables that are invariant, and you assume that the frame observable is something that transforms covariantly. And once you've done that, you can conclude that any operator that arises in this sense is going to come up from an equivariant function. And this gives you Yen. Yeah. And there are, yeah, I mean, so basically, like, as I mentioned, like any two of those implies the third one under some assumptions, but they're usually weak. Like the group is compact or the action is like nice enough and stuff. So like in physics, basically, if you want to use these tools, well, obviously this is a choice, and like most of us here, they don't make this choice. I do, but then this is really what you should be doing. That's my belief. Yeah.
Then let's thank Jan again. Jan.
Oh, sorry.
Okay, then our next speaker is Lin-Qing Chen, who is a postdoc in the group of Caslav Brukner. Please.
Thank you. Thank you very much for Rick for making this happen, and thank you for all the audience still here despite you are already very hungry. So I'm very excited to share about this project, which will appear in arXiv very soon. It's the quantum reference fields transformation in linearized quantum gravity. So the motivations are twofold. Okay, good. First, it's about the diffeomorphism in quantum gravity. We know that diffeomorphism invariance lies at the core of general relativity, with profound implications for the physical observable, locality, symmetries, and the notion of time. It is one of the key conceptual and technical challenges. That's why quantum gravity is so hard. And it manifests in different ways in different approaches. So for instance, in canonical loop quantum gravity, it manifests as the challenge of solving the Hamiltonian constraint. In the path integral formulation, the spin form approach, it is the challenge of, through coarse graining, get the correct renormalization flow to reach the correct continuum limit. And in the very recent approach of celestial holography, diffeomorphism plays a very strong constraint on the S matrix. And this is related to the asymptotic symmetries as the imposed world identity on the scattering process. So since quantum spacetime is unlikely to admit a fundamental description in terms of differential manifold, we need to think deeply and re-examine what we mean by diffeomorphism in the quantum gravity regime. So the second motivation is about background independence. So if we want to construct a relational description of quantum spacetime, what we can be relative to? So in the universe, we have quantum gravitational field and quantum matter field. How about using quantum matter fields as the reference system? Due to the universal coupling of gravity, this tells us the reference system enters the gravitational constraint and they backreact to the quantum spacetime. And this is especially fundamental and might not be negligible when we reach this quantum gravity regime compared to classical general relativity. So the key question of this project is that how to formulate quantum reference frame transformations associated with physical fields, which are able to enact local transformations on the gravitational state. So Caslav already gave an excellent introduction for the reference frame. I only want to mention that this project is built upon one of the first example in the perspective neutral approach, which we consider 3 particles. The system, the dynamics is imposed by a primary constraint that the sum of momenta are 0. Then the main insight in this work is that they design a constraint trivialization map defined on the whole kinematical Hilbert space. It's a unitary map such that transform on the constraint, it gives us the momentum of the frame. So it's set from the constraint to be 0 to be the frame's momenta to be 0. And then acting on the relational observable QA minus QB, which is translation invariant, it gives us the coordinate of B in the perspective of A. So switching internal perspective, one can connect this with the earlier work by Flaminia, Caslav, and Esteban on switching the perspective between A and C, and then the description of the system, the relativity of entanglement, etc. So the perspective neutral approach also has been developed for unimodular Lie group. However, this is not applicable for diffeomorphism. And in fact, for the field theory context, if one look at lattice model, for instance, lattice QED, due to the group of gauge transformation is compact, one can still use the techniques in the previous paper. However, for quantum gravity, we need to develop new techniques. So the challenge would be how to make sense of the trivialization map in the gravitational system. And so, since Caslav already gave so much insights in the introduction, I only want to add one point, is that the quantum reference frame program has, in my view, has a lot of resonance with some perspectives of the cubism. It's not the cubism in the quantum foundation. And so probably to understand the quantum gravity, we really need to patch different perspectives simultaneously on the same canvas. Okay, so that comes into the construction. We use a set of 4 physical scalar fields as quantum reference field. And we relate the spectrum of the field operator with the usual notion of the coordinate. How this is constructed explicitly. So you learned in the GR textbook that the usual coordinate is constructed by a map from the open set on the manifold to RD. And so here you can also, if a coordinate system can globally parameterize the manifold, you can also identify the equal time hypersurface given by such fictitious coordinate. And here we map the open set to the Hilbert space, to the operators of a physical field. And so on each equal time hypersurface given by the S0, one can look at the field basis of such a quantum field. And so we require the eigenfunction of this field basis to be the smooth and local invertible. The reason for that is that this gives you a resolution, sufficient resolution to define a coordinate for this region. So for instance, if I use a constant scalar field in this room, it can be a reference, but it cannot resolve the locality much. And so here we particularly use the x as symbols in the analogy with coordinate, but it is different from the notion of the coordinate in general relativity. So here you can see that we have the 3+1 decomposition of the manifold with 2 physical quantum fields, XA and XB. And we will study the transformation of the perspective between them. So the quantum state of the reference field can be in the arbitrary superposition of its eigenbasis. And they are physical fields that can back react onto the space-time, they enter the gravitational constraint. The sandbox we are playing with this idea with is the simplest model in gravity that the quantum theory can be exactly solved, which is the linearized quantum gravity. So one can perform the canonical quantization for the metric perturbation. So the image illustrated this canonical decomposition as 3+1 decomposition. And for the audience who have never heard of it, you can imagine a lasagna, and there is a gauge transformation on each sheet of the lasagna, and the N and Ni tell us how to connect between the different slices, and the slices can move relative to each other, and you can put a toothpick in the middle to tell us how to identify the spatial point on which point time evolved to which point and how quick the clock runs. So the canonical variable is the metric perturbation and the conjugate momenta. And the primary, this N and Ni, the other two Lagrange multiplier, has conjugate momentum 0 as the primary constraint. So here I'm going quickly because the technical details you don't need to focus on. You only need to know that at the end, you get a quadratic Hamiltonian evolving on a Minkowski spacetime, which is the following, and it can be exactly quantized. There are 4 constraints generates diffeomorphism symmetry. They are the gauge symmetry of the perturbative gravity. The scalar constraint, this is the reminiscent of the time of the Hamiltonian constraint, which the Hamiltonian constraint gives the time representation invariant of general relativity. And the Ci is the generator of the spatial diffeomorphism. Crucially, here, the stress energy tensor has all the matter components as well as the quantum reference fields. Okay, so very good. We need to emphasize that not any physical scalar field can be the reference field for linearized gravity. This is because we want to express the metric in this perspective as if using it as a coordinate. And this transformation needs to respect the perturbation expansion. After the transformation, you still get Minkowski plus the perturbation. Therefore, this places the constraint of how fast it needs to evolve with time and the spatial derivative as the order h. Order h is the order of the system, so it is not small. And given those conditions, one obtains an expansion of the stress energy tensor so that the leading order is actually proportional to the canonical momenta of the field. This step is crucial for us to perform QRF transformation. Otherwise, the construction, at least we didn't figure it out how to work without this condition. So for instance, the energy part is so all the stress energy tensor is a sum over the 4 scalar fields. And at the end, the leading order is the canonical momenta of the corresponding I or 0 component of the field. The observable we are looking at will be the physical observables for gravity. As we know, due to diffeomorphism, there's no local physical observable. And so in gravity community, there's a lot of work on defining observables in terms of physical value of the reference, but not on the manifold. This is very resonate with all the relational approach that has already carried out in the institute. And so for a classical coordinate field, we need to find its inverse map. Namely that I know the value of the field, can I map it back to where was its coordinate or the point of the manifold? This inverse map is defined by this chi, and through this, one can build the diffeomorphism invariant relational observable as the following. So it is, for instance, for scalar, it will be the scalar field evaluate at the point where the reference has the value y. And one can check this such type is diffeomorphism invariant. Similarly, for tensor field, for instance, for the metric, one needs to take into account the Jacobian transformation, which has the part of the derivative of this inverse map. Going to the quantum coordinate field, we need to define the inverse map through the operator. And the inverse exists thanks to the fact that initially we define each eigenfunctions as smooth and local invertible. Notice that although this is a strong requirement on what kind of field can serve as quantum coordinate field, we expect this only hold, for instance, in a small region around, for instance, an inertial falling observer, therefore observing the perturbative gravity with the validity in this regime of certain reference field. Okay, now we are ready to reduce the diffeomorphism invariant observable in the perspective of the physical reference. So we define the trivialization map as the following. So although the equation is long, the structure is very simple. It is the coordinate field, it is the quantum reference field times the constraint that removing the contribution of the reference field. And as a result, this gives us, acting on the constraint, it tells us the stress energy tensor in this frame is 0. And the physical state becomes that the stress energy, the frame's physical state tensor factors out from the rest of the relational state. The scalar field relational observable expressed in its perspective becomes as following. As you can see, this is really analogic to how coordinates work. However, here we are transforming a diffeom invariant observable in the perspective of A, it reduced to psi xa, as if this quantum field is really like a coordinate. And this step only works if the reference field enters the constraint. That allows us to do this reduction to the perspective. And similarly, as the relational gravitational field, one can also reduce the accordingly, similarly as the scalar field. So one can perform gauge fixing by projecting on specific state of the coordinate field. And there you really get psi xa as if a normal coordinate. Am I good with time?
5 more minutes.
Great. Then one can transform the perspective between the two coordinate field. And in general, one can have any operator in the perspective neutral space and to change physical configuration. But one is the identity is really analogic to the passive diffeomorphism. And then for scalar field, it changed psi xb to psi xa, similarly asymmetric tensor. I need to emphasize that it's a very interesting feature that there's a mixture between gravity and matter Hilbert space. And this comes from the familiar relative subsystem relativity that's already being explored in the community. However, it becomes more drastic in gravity because gravity and matter become a frame-dependent separation here. And the relation with the standard diffeomorphism is that I will need to go fast here. The punchline is the the reduced observable is diffeomorphism invariant. However, the transformation between perspective is non-trivial. Therefore, it is conceptual and physically different from the standard diffeomorphism or superposition of diffeomorphism. At the end, we want to make sense of those observable operationally. So the key question I want to know is what type of physical observable in quantum gravity are in principle measurable. So we can construct a measurement scheme through coupling the probe field with a clock as a quantum control to measure the system. And the key step is that you define the interacting Hamiltonian by those relational observables so that it preserves the constraint. And in the perspective of A, the interacting Hamiltonian becomes the following. Such Hamiltonian entangle the probe and the state, and at the end, when you do the projection, it will still stay in the physical Hilbert space because the eigenbasis is transformed by a relational quantity. In this way, the psi xa is operationally accessible. So in summary, we generalize quantum reference frames to fields by associating them with physical fields which are included in the gravitational constraint. And the relational measurement scheme relative to quantum reference field can help us to understand the reduced observable and how to access them operationally, at least theoretically. As a quantum reference field, transformation defined here are given by dynamical internal quantum subsystem rather than fictitious coordinate field or vector field, external vector field. This leads to a transformation that is conceptually and physically different from the gauge symmetry in gravity. So then we see an explicit mixture of the gravity Hilbert space and the quantum reference frame Hilbert space, which is very interesting. So the outlook mainly have 3 directions. So first, the direction is identifying the new physical effect coming from the quantum nature of the frame, understanding the algebraic structure and the notion of covariance, how this is different from the usual GR notion of the covariance. The second direction is a complete formulation of the covariance relational measurement in quantum gravity, and utilizing quantum reference fields to formulating observers or help us bringing insights into the current efforts on experimental verification of the quantum feature of gravity. This I don't have time, but I can elaborate more after the talk. The third direction is connecting to the broader approaches of quantum gravity. For instance, edge modes, asymptotic symmetry, and eventually we want to apply this relational formalism towards a non-perturbative regime. With this, I thank you for your attention.
Hi, thank you, Lin-Qing. Very nice. So, I'm a bit confused about the conceptual direction here. So you talked about background independence and diffeomorphism and so on, but then the analysis was in linearized quantum gravity, right?
Yes.
Where you have a fixed background,
Yes.
and also what is called gauge symmetries are not really gauge symmetries, is some infinitesimal diffeomorphism that preserve, that act like gauge symmetries, but only insofar as you're not breaking the linearity, right, of the
Yes.
approximation. So it's just
we're looking at-
infinitesimal diffeomorphisms.
Yes, infinitesimal, which is the gauge symmetry for perturbative
So
gravity.
in this sense, it seems to be the context is somehow less than electromagnetism, just with 2 indices, 2 forms instead of a 1 form. So I'm a bit confused how this can be pushed towards something non-perturbative. Are the constraints that you're talking about things like the Hamiltonian constraint or things like the Gauss constraint?
Yes, so here, thank you very much for the question. So initial motivation, but this project is not to solve all the questions in the initial motivations. So here, for the background independence, we want to carry out a relational approach. But here we have a fixed background, but the relationalism is for the quantum system defined on it, which is the perturbative gravitational field. And here is already, they gives the perturbation onto the quantum space-time, and it's already a constraint system. From the lesson we learn here, we can hopefully, in the future, apply to the general Hamiltonian constraint, which here already need to involve a little bit of the surface deformation algebra from the whole canonical gravity. And to understand how this reduction carries out with the whole nonlinear Hamiltonian constraint together with the vector constraint, it will be a crucial step. And then, so this will be a very ambitious direction. A slightly easier in the middle step is that one can apply this, for instance, together with equivalence principle. Then with a local inertial observer, around the local inertial observer, it is approximately Minkowski and with some perturbation. In this way, such a framework still can work. And then one can connect the different inertial observers. And this can still make sense in the context when we do not have the global perturbative quantum gravitational state. But using perturbative gravity is like the first sandbox we are playing with this idea of how to define the reference fields to make sense of the gravitational field.
Okay.
And also I want to add one more point is then with some conceptual point being clarified, hopefully this can be directly used in certain already established quantum gravity model. Because the constraint is already, like for instance, spatial d-field constraint is solved in the loop quantum gravity, not the Hamiltonian constraint.
Okay, then let us thank Lin-Qing again. Okay, then it is my great pleasure to introduce my PhD colleague, Ofek Bengyat, who is a PhD student in the group of Marius Christodoulos.
Hello, everyone. Thank you for the organizers to making this happen. I'm going to talk also about something very related to quantum reference frames. Namely, I will show how quantum systems, when you use quantum systems as reference, you get the transformations between them to be something called quantum permutations. I will start by a very neat argument. I will try to not make this too technical talk. This is a work with my PhD supervisor, Marius Christodoulos, and with Caslav Brukner. So let's start with an executive summary. So I will start with something we all know, that if you use classical fields as reference systems, you get that the transformations between them are diffeomorphisms. Then I will apply the exact same logic to when you use quantum fields as reference systems. And then we will see that what emerges as the transformation are those quantum permutations. We will then talk about their meaning and their difference and relation to the quantum reference frames we already know, the quantum controlled ones that we had heard about until now. So they generalize them, and we will see exactly how and in which regime they reduce to them. And then we will also talk about the invariance of the physical laws, about the covariance of the transformations of the different fields that constitute physical laws. And we will show that indeed physical laws are invariant under those quantum permutation transformations. So let's start with what we know. Let's say we have two classical reference fields. We call them chi, chi1 and chi2, and one field of interest that we call phi. Now, those q's that are defined on is a mathematical beast, a manifold. And we don't have access to this phi q and chi I of q. We only have access to our field of interest measured when the reference fields get some, take up some value, x. So this is what we can measure, the field relative to a reference. Now, how do I move between references? Pretty trivial. You concatenate those two reference fields, and you get something that we call a diffeomorphism. Now, to do this, I have to assume that the reference fields are invertible. This means that, as Lin-Qing said, we have enough resolution to describe space-time and move between the references. Good. Now let's do the same thing, but in the quantum. Let's say we have two quantum fields that we use as reference, chi I of q. Now they have a hat because they're operators, they're quantum. I do not make any assumptions about the dynamics of them. I do not make any assumption on whether there is gravity there or not. I mean, before in the classical case, this simple argument, if you can call it an argument, works regardless of if you have gravity, if it is linearized or not, and completely independent of the dynamics. It's a kinematical concept, reference frames. Now we also have a field of interest also in the quantum case. It also has a hat. And they're also defined on some mathematical beast that for now we take, for now I mean for this talk and this work, we take as a finite set. Now, what is actually measurable is, again, the field of interest, the value that it takes when the reference field takes up some value xi. Now, once you have just assumed this, you get, after a bit of linear algebra, that the transformation between those two, and now we will see this bit of linear algebra, but you get that the transformation is, it looks like this. It contains those u, x2, x1, which are operators, and they constitute a mathematical object that is called a quantum permutation. This quantum permutation is determined uniquely by the fields of reference chi I that you chose. Okay, so how did we get here? this will be a bit technical, but this is what lends the credibility to what I'm saying. So even though it's a short talk, I will talk about it for a second. So those reference fields, this field of interest relative to the reference fields phi I of xi, what does it mean that it is relative to chi I? It means that it takes up the same value as the original field defined on the mathematical beast, phi q, whenever the reference field takes this xi value. Yeah, exactly like in the classical case. So it means that when we are in an eigenstate of chi I with the value xi, then the relative field at xi is equal to this q, where chi I takes the x. Now, this is simple. This is sufficient to define uniquely how the relative field, or the phi relative to chi I, looks like, and it looks like this, where those p's are the major ingredient. They are the projection on the xi eigenspace of the operator chi iq. So chi iq is a Hermitian operator. It is diagonalizable. This means that it has projections, unique projections that project on its eigenspaces. And if you use those unique projections, then you exactly see that you can define as phi as having the value f of, you can define phi to have the value of phi of q exactly when you are in the subspace where chi of q takes x. And from this, the way to the transformation is very short. You see that the transformation, the quantum permutation u x2, x1 is defined by the sum over the multiplication of those projections. Now, there is maybe a more neat way to write this as a formal matrix multiplication. You take the field phi relative to chi I, to chi 1, you put it in a vector. Relative to chi 2, you also put it in a vector. Turns out you can write U as a big matrix, and this is the relation between those two fields phi relative to the different references. Now, the meaning of the ux2, x1 that defines the transformation is very simple. It is also a projection, an orthogonal projection on the Hilbert space, that projects the state onto the subspace in which one reference takes the definite value x1 if and only if the other reference takes the definite value x2. So this is what makes you go locally into something definite. Locally, x1 and x2 are interchangeable, at least in this subspace. And then if you just sum over those subspaces, you can do a definite transformation everywhere. So this is the idea behind why those objects are quantum coordinate transformations. Okay. Now, how does this relate to the quantum reference frames we know? It turns out that when you take the reference fields to commute with themselves at all points, which is usually not the case with quantum fields, but let's assume we are in this case. This is the case you get when you, for example, assume no dynamics for the reference field. So you don't assume any equation of motion that then enforces some commutation relation. And another case is when you do use a general field, but you just look at the limit when h bar goes to 0. This also makes all commutators that I know in quantum field theory to go to 0. And in those cases, because you have this commutation of all points, you can define a common eigenbasis, the configuration basis of chi. Now, we all know that the configuration basis of chi, you can define it on a space-like hypersurface. Because on a space-like hypersurface, you always have commutation in quantum field theory. But here, this is stronger, because we assumed we have commutation everywhere. So you get this configuration basis. And this reduces the quantum permutation to a quantum-controlled permutation, which is exactly what we know from quantum reference frames. Maybe the most elaborate version of which is in this paper. About half of its authors sit here. So you just control over the configurations, and in every configuration you have, in every control branch, you have a definite picture, and then you can apply your definite diffeomorphism. So it's just superposition of classical realities or of definite realities. But this is just a very restricted special case. In general, what happens with quantum permutations is that, well, your reference fields do not generally commute. And this is why you cannot describe them as a superposition of definite diffeomorphisms. But if you want to force it into a mathematical form that is maybe not convenient for calculations, but is convenient for intuition, you can write this form. In this form looks very much like a quantum-controlled transformation, just that we have the sum over x. So it tells you sum over the points of the first reference, and at every point, decide where it goes to according to a quantum-controlled transformation. Now, this is not like quantum reference frames, because in quantum reference frames, you don't sum over the points. You say, first control, then according to the control, perform a diffeomorphism over the entire space. Here, I perform a transformation of every single point according to a different control. Turns out that it is not the same exactly because of this non-commutativity, exactly because of the lack of the mutual diagonalizability of all of the field operators everywhere. This is why we call this form beyond quantum controlled. Okay, now the last part is the invariance of physical laws. So we will now see that physical laws, a representative example will be the action of a scalar field on a curved space-time, remain invariant under those transformations. So this is the action of a quantum scalar field on a curved space-time. But as I said, we are working in the discrete for now, in a finite set. So in this context, this is how the action looks like, where I define the discrete derivative as, well, just being the difference between the field values over the distance between the points. This is this delta of phi 1. And this G is some operator, and the only assumption that I make about it is that it is Hermitian, and that it is symmetric to the exchange of the last two arguments. Now, why do I have many arguments in those functions? So phi is a derivative, so it is delta phi is a derivative, so it depends on the point, but it also depends, like in general relativity, on this index mu that it has. So it tells you what is the difference in some direction related to mu. Here, I turned it into another argument because we are in a discrete. So it tells you what is the difference between x1 and x1u. U is like mu, yeah? Now, for G, we have another argument because it is a tensor. It describes the relation between a point x and its closest points in directions mu and nu. This is why here I have two arguments. Okay, so what happens to this discretized quantum scalar field action when we move quantum reference systems? Now we need to take a bit of a tangent, because in general relativity, you don't just apply any invertible transformation. You need it to be differentiable in both ways, to be a diffeomorphism. But what does this condition mean in the discrete? Well, continuity means that if x is sent to y, then something close to x will be sent to something close to y. Differentiability means something very similar, just a bit different. It means that if a point that is close to x in some direction, like if x is sent to y, then a point that is close to x in the direction n will be sent to a point close to y in a direction that is determined already by x, y, and n. Where we do see it is something we know is that in multivariate functions, the derivative is this matrix that takes the direction of the difference from x to a nearby point and gives you the direction of the difference between y and the nearby point. So in this spirit, we will now define what it means to be differentiable on a quantum permutation, for a quantum permutation to be differentiable in the discrete and quantum. So assume that we have a quantum permutation that sends x1 to x2. Now we want to know what happens to a point close to x, x1u. So x1u will be sent to some point close to x2, x2a, but it can only be sent to a point that is determined by x1 and x2, and this direction n, which is here the x1u. So this is exactly what we had here. Whoops. This is exactly what we had in the multivariate function. But so we have dependence on x, on the point close to x, but we don't have dependence on y here because y is determined by x. It's a classical function. The only difference to the discrete quantum definition is that you also need the image of x because it is not defined completely by x. Okay. Now, after you restrict only to systems that are differentiable under this definition, you get that from the transformation rule of the fields that we saw before, the transformation rule of the derivative takes this form. Now, this form is very similar to the form of the fields. It has the quantum permutation projector in every part of the sum, but it also has this J, which is like a generalized Jacobian. It is the difference between this quantum differential divided by the difference between the 2 points. So it is just like the Jacobian, just defined on the case where x1 goes to x2. Now, if this is similar to general relativity, let's also assume that the metric has a similar transformation rule. So it has 2 Jacobians because it has 2 tensor indices. And once we assume this transformation rule for the metric, we see that the metric transformed under this transformation rule is such that the action remains invariant under those differentiable quantum permutations. So physical laws are invariant under, at least in the discrete, under those quantum permutations obeying differentiability. So we saw that quantum permutations emerged from a very neat linear algebraic argument as the most general transformations between 2 reference systems that are quantum fields. They reduce to the known quantum controlled reference frames when you have commutation of the fields everywhere, which can be seen as a limit of h bar goes to 0 or a dynamicless field. The difference between them has to do with locality and globality. So quantum reference frames are a global diffeomorphism put in a big superposition, whereas quantum permutations go and make a superposition at every point. This is a bit reminiscent to the difference between special relativity and general relativity, as diffeomorphisms in general relativity are locally deformable, whereas boosts are not. We saw then the covariance of the fields constituting the physical laws, making the physical laws invariant, of course, under this differentiability assumption. And this differentiability assumption is now part of the outlook, and the hypothesis about the outlook is that when we go and do this in the continuum instead of the district, where all the sums will become integrals and, of course, a more rigorous mathematics will be applied, we expect that this differentiability condition to not be something that we impose from outside, but something that naturally emerges, because diffeomorphisms, if we take classical fields that are usually differentiable, you concatenate them, you get something differentiable. So quantum fields are also differentiable. You concatenate them in this way to make quantum permutations. Well, in the continuum, I expect that the quantum permutation will also be differentiable, exactly in that sense, or in a more general sense than we saw today. But this is just an hypothesis for now. Thank you very much.
So time for a quick question. Lin-Qing.
Thanks a lot. So if I take a genome quantum field, but with microcausality, so space-like commute, but of course, a long time is not. And in this way, I would actually get a time-dependent quantum control. So it seems to me that this permutation really comes from your quantum field on a spatial hypersurface are not commuting with each other. And what would be the physical motivation for breaking the microcausality?
There is no physical motivation to break the microcausality. This is why quantum reference frames usually do not describe the transformation between two quantum reference fields. You have to go to quantum permutations because, as you said, there is non-commutation.
But on the spatial hypersurface, they commute.
So I'm not working on 3+1, or I'm taking everything at once. I do not.
Oh, you don't separate.
I don't make any foliation. I'm just saying, let's take the entire manifold and define a field of the entire manifold and use it as a coordinate field. Yeah. What happens when you make a foliation? I don't know.
Thanks. Yeah, we can discuss.
Let's bring Ofek again.
Yes, it works.
Then our final speaker for the first session is Bruna Sahdo, who is a PhD student in the group of Esteban Castro Ruiz here at IQOQI.
Okay, thank you, Emil. Thank you to the organizers. So this is yet another presentation about quantum reference frames, not only related, but really about it. And I'm going to talk about the adding, removing, or the compositionality aspect of quantum reference frames. So, hopefully, the last talks that we had, especially Caslav's talk, already motivated very well that why we study quantum reference frames and where do we apply it in connection with quantum foundations and gravity. And one reason for studying compositionality is that we want to know what are we doing to subsystems in those theories in which we apply reference frames. We want to know how to interpret them. But another reason is for the foundations of reference frames itself. I would say that compositionality is one of the main, one of the core things that make the definition of quantum reference frame transformations and perspectives a non-trivial thing to do. So, for example, if we have a classical case here in which a classical reference system serves as reference for the position of S, system S, and there is like this definite position here, we know from, for example, an external description how to transform to another reference frame. You don't even need to put it here. We know if we want to go to a reference frame that's spinning or something, we can just describe it by relating these relative quantities. If we want to jump to a reference frame B that is like in this position, we would just make a subtraction of these relative distances, right? Now, if we want to talk about, we want to generalize this directly to a quantum reference frame, the thing that would be like most straightforward to do is to make a generalization of this subtraction that we do. Something, a rule that would say what is the position of S with respect to B would depend on the distance relation here and this distance relation, right? So basically, this would imply, by just normal quantum mechanics, that if we say that the perspective of the system is just this state, we are mapping the perspective of A looking at S to the perspective of B looking at S. And this would take, in general, like some pure state to a mixed state. If we define reference frames perspectives like this, we would have a non-reversible transformation. And this is not desired, of course, if we want to do an entire framework in which we want to be able to jump between reference frames. We want them to be reversible maps. So there is a nice way around this, which is what was already done in the reference frameworks that were cited here before, in which we just say that actually when we have quantum reference frames, or maybe even just probabilistic reference frames, we don't map from S relative to A to S relative to B. It doesn't work. Instead, we say that the reference frame to which we want to jump is included in the perspective of A already, and A is also included in the perspective of B. If we define perspectives like this, we can always define reversible transformations. And we solve this problem of reversibility. However, later it was shown that the problem of reversibility in this sense is not completely solved by doing this. Because imagine, maybe according to this external description, that there is another system. So if we do this, we have, again, a reference frame transformation between A and B that is reversible. However, if we want to talk about the reduced subsystem again, what do we expect? That the reference frame transformation between A and B for the reduced subsystem is a reduced version of the reference frame transformation for the entire thing. We would expect that, especially if we are describing with an external observer, right? However, for this to be true, we would have to take reduced states in this subsystem to transform reduced states. And this, you can show that this cannot be reversible again. So what's happening here is not necessarily a paradox, but a tension between reversibility and compositionality. It looks like very much that we already know that the transformation here, we can define a reversible one, but it cannot be seen as a restriction of the bigger transformation. It really looks like you have to choose between one and the other. You want to choose whether you want to have a compositional transformation and then the restricted ones will not be reversible, or you want to have reversibility and then you cannot talk about setups inside of the other. But this is not true. This also can be circumvented. So in a recent framework, it was shown that you can make actually quantum reference frame transformations that are both reversible and compositional in the sense that I'm talking about. And actually, the way they solved this reversibility issue is similar to how the former reversibility issue was resolved, which is basically saying, well, this here is not reversible, but if I add extra degrees of freedom here and extra degrees of freedom here, I can recover reversibility. But they do it in a clever way, such that the problem doesn't appear again every time I add a new particle to my subsystems. Therefore, they make this reversibility and compositionality possible with this same kind of solution. And these extra degrees of freedom that enter here and there are usually called the extra particle, and the formalism usually coined the extra particle formalism. Okay, so this work is actually done on top of this extra particle formalism, because it's where it makes sense to talk about compositionalities and adding and removing systems at all. So we thought it was a good idea to make a concrete, to understand concretely how the compositionality looks from the perspective of a reference frame and how this thing can be consistent, right? So at first, I have to introduce how to use the formalism. And this is a little bit difficult to do quickly, unfortunately. But I'm going to try to give like a recipe or an algorithm of how to use the formalism without much entering into it. Basically, when we want to define QRFs using this formalism, we need to begin, we need to begin with an external description of two systems. And I'm going to talk about the fact that we are using external observers afterwards. We need to have a symmetry group that in this case that I'm talking about, are usually talking about translations, and they have to have a representation in each of these spaces. Then, the idea of a reference frame perspective is that it is an invariant description, internal description, that is made relative to one of the subsystems of that setup. So we need both a notion of invariance and a notion of perspective, or relative degrees of freedom. And this we borrow from quantum mechanics, or from the standard way of defining these things. So a notion of invariance, if I already have a group and a representation, like global translations, I just say that an operator is invariant if it commutes with every global translation. And this is the same as writing that it is preserved by this general operator here that is called the G twirl. Now, to define relative quantities with respect to one of the systems, we need to ask that this system has well-defined notion of position, or for the case of position of translations, that it has well-defined cats of position or cats of the group, of the symmetry group. Here I'm going very quickly just to, if this exists, then we can define this map. And this map is just something that looks where A is and translates B accordingly. This map is used in the formalism like a passive, you can think of it as a passive transformation that takes the Hilbert space from this tensor product structure to this other tensor product structure. And this here, on the right-hand side, we get the relative degrees of freedom of B relative to A. On the left-hand side, we have everything that's left. So these two notions are independent. We can apply them independently. But basically, if you want to talk about an operator described in the perspective of A, you apply this, and then you apply this. So as an example, for a finite case with positions on a circle, if you have A in a definite position 1, if you have B in a superposition here, I can jump to A by using this map that I talked about. And basically, in this formalism, we have the state in the perspective of A here. And it is composed really of two systems. Again, the perspective here, it is what you expect is the relative version of this state minus 1. And here is, in this case, is mapped to the maximally mixed state on this factor. And I change here the factorization of the prime to the bar to indicate, just to indicate that this is an invariant operator here. So this is what we call the extra particle space and what allows for reversibility. All the invariant operators, they are not relative, and every time I describe a perspective, they are present there so that I can transform accordingly. Okay, so two things that are important to know for this presentation about the extra particle, that is that for this example in which we have a notion of distances and position and momentum, discrete position and momentum. First thing is that it encodes the total momentum. So basically what this UA map does is to map the total momentum PA plus PB to the left-hand side of my factorization. And this here is the general form of an allowed operator in the perspective of A. It's just a superselected in the left-hand side. The other thing that it's actually related very much with this is that the extra particle has some information about the outer state of this frame. So for example, whenever this frame is in a classical sharp position or in a mixture state of positions, this maps to the extra particle in identity over N. This is always true. Therefore, if I could access this from this perspective and see it's not here, I would know that my frame is definitely not classical. It definitely has coherences from an external view. And this is a weird thing because it looks like there is external information available from inside. And it's actually a consequence of the fact that the Stoy model only asks for invariance under translations. So since you're not asking invariance under boosts, momentum information is available, and coherences in position state are also information about momentum. So this is available, but still weird, right, to have external information inside here. It really depends, it really seems like the fact that A is classical or not would depend on who is this external observer. So we can do a consistency check, which is our first result. Is this dependent of an external observer? Is the external observer important, really, that we fix in this formalism? And we can show in a very general way that no, basically, that any external observer, very general external observer that we could define with respect to the first one would arrive at the same conclusions. And this formalism is cool because it allows to describe the use of itself. Here, every time we have a description of external observer, we can embed it in very different ways. We can embed it in a non-unique way by saying that these are actually relative degrees of freedom with respect to Eve and completing the extra particle of Eve. What is interesting is that each of these observers has a different notion of what invariance means for A and S, because they have different relative systems. But nevertheless, they arrive at the same conclusions of what is the form of operators and what is the form of states of this invariant subsystem, whatever they call invariance. And what is cool also is that you could introduce another agent here, also described by this bigger external description, in any state quantum, even entangled even with respect to if, as long as is something that is compatible with what you had before. That doesn't, that is not against what Eve is seeing, right? And then you can show that it has a different even notion of invariance, but you can show that E1 applies the formalism, or E2 applies the formalism to this subsystem. Regardless of what their state is, they arrive at the same operators and states. So this is a first of 3 results that hopefully I will have time to talk about. This is like a consistency check, but also guarantees that I have really generality. Even though I'm fixing an external observer in the beginning, I have a big generality for what I'm talking about inside of this subsystem here. And we can use that actually to talk consistently about adding and removing subsystems, which is the second step. So now that we talked about compositionality of external observers, we're going to talk about compositionality inside a perspective. So we're going to use the spaces of Eve now for this, knowing that everything is well defined. When I have only a reference frame looking at S, I have the transformation that defines the perspective of A here, and it is a unitary. If I say that I have another system pops up, I can use the external description to say another system popped up. And I assume from the external description, I can use quantum mechanics and embed my operators like tensor identity, another system pops up. So now I have also, if there is a representation here, I have a notion also of jumping to A in this second, in this extended setup. And therefore, with these maps, I can define an inclusion of the old perspective of A and the new perspective of A. So I can talk about, what is the state of the extra part, the old extra particle of A inside the setup. I can talk about things like this. So since I can do that, I can define a valid state extension as an extension of initial state that does not change the reduced state of the initial setup, right? I can define it like this and ask then, when can a new system appear in a tensorized state for this perspective of A? Why am I doing this question? Because I know that there are some restrictions here for what can appear. And in particular, I know that for when I am in a normal quantum situation, describing a quantum experiment, my experiment is always compatible with another system in an independent state, tensorized, right? So I want to know how does that work for a QRF. And basically, there are restrictions for subsystems that can appear tensorized here without nothing changing in the initial setup. And we have a full characterization of it that will appear in a paper soon. But an important thing here is that you can only do this for arbitrary gamma, add arbitrary states gamma, if your extra particle already begins in the identity over n. So again, this special state is appearing here as something that reminds us of how our classical reference frame perspective looks like and how it behaves. So this is another feature that we expect when we have a classical reference frame, that we can add things arbitrarily. So since this is a very special state, I can enter very quickly into our third part of these results. There are, acknowledging that this is a very special state, we can ask, is there a transformation that is natural and I can apply to any initial state of a perspective that gives me back a state that is in the identity of the extra particle? a state that is familiar to me in which different systems can be added, or that just looks classical, right? Classical-like. And the answer to this is yes, there is, and we call this procedure classicalization, but you have to do an extension of this. So we'll have an extra particle that is identity over n, but in an extended system. So it goes through different steps. First, we add we internalize the external observer with an extra particle that is the extra particle that we want. Then we change from the perspective of E to that of A, and we apply this classicalization map. That is what allows us to transform the state of A, of the extra particle, in the identity over n again. After this procedure, it's guaranteed that the extra particle is in this state again. And as a bonus, this coincides with the perspectival jump of the other reference frame frameworks that were presented before. But basically, if we are already in this state, why not add something, right? We can add an arbitrary state gamma tensorized in a perspective like this. And we can actually do that and reverse the procedure of classicalization. So we can classicalize, add something there, and then declassicalize. And if we do that, we get something like a effective update rule that always gives me something tensorizing gamma. But of course, as we showed before, this cannot be a valid extension. Something changed about the initial system so that this gamma can appear here. However, it has an interesting interpretation. If you remember what I said before, the extra particle decodes the total momentum, degrees of freedom. So this extra particle here is the momentum of A plus S, and this extra particle here is the momentum of A, S, and S3. And what I'm saying is that the profile of momentum of the state of momentum continue to be the same, but now there is a third system here. Like I have the same value of momentum, but now there is a new system. What is going on? This is very much compatible with an internal procedure or internal adding. You can think of A as classically as a little cannon that already has a system here, and they are in this P total. If this cannon only recognizes a new system after it's shot, it's possible that the entire state of the system is still in P total, even though now there are 3 systems. Of course, this also implies that the reduced system here, A and S, changed momentum. It was actually received a recoil. So this transformation basically shows how you could do some internal adding thing. And okay, for the quantum case, I mean, this is the classical analog, but for the quantum case, this also means that this adding is some adding that respect the coherences of the state, or could be seen like this if you look from outside, you know, the update rule. I think there's a lot of interesting things still to explore about this, but yeah, I think that's what I had to say. So, thank you.
Okay, one very quick question. If there is one. Okay, if not, you have the chance to talk to Bruna now in the lunch break. In the spirit of morale, I suggest we stick to the scheduled 1-hour lunch break. So we will reconvene at 2:45. You're welcome to use the IQOQI kitchen, which is 1 floor up. There's no food there, unfortunately. You have to buy or bring your own, but feel free to eat there. And I also encourage all our guests to grab local people, speakers maybe even, not only because they're interesting and fun to talk to, but also so that they can let you back into the building. Okay.
Hello and welcome to the second session of the ISRQI circuit. We have here now Marius Christodoulos, and it's a pleasure to have a look into our tabletop quantum gravity experiments.
Thank you very much.
You have a microphone yourself.
I have this, right? It works? Yeah. Okay, so thank you very much. Thank you, first of all, to everybody for organizing. So did Jeremy made his way in? Are they? Oh, okay, good. All right, so for those that came to my defense of the habilitation thesis a couple of weeks ago, I'm sorry, but I didn't have time to make a new slides. It's a more compressed version of that. I will skim quickly through like the first part, where I'm gonna set the stage to tell you some of the things that we're doing now, and I've added a last part, a couple of slides where it's things that are actually happening now with Nikolas and Emil, students at my group. All right, so flash reminder, let's fix this mental picture in our head for the rest of the talk. You all know what this is, I will not go into it much. It's the entanglement through gravity experiment. You put two masses in superposition, you start with a not entangled state, and the simplest way to see what's going on is in these branches that are close by, you get a non-negligible phase. If that phase is non-zero, here's the entanglement entropy, you get an entangled state. We talk about the importance of this experiment. There's a big debate about it, but intuitively people sort of accept and talk about it in the following terms, that what's happening is that in each branch, here whether it's left-left or right-right, you get a different space-time, right? So you have these ChatGPT generated space-times. Each one has a different distance between the regions of curvature, which is where the mass is sitting, and two space-times that have, let's say, this one and that one, because the distance is different. They are not diffeomorphically equivalent. These are different space-times. And you imagine that what this is sourcing is some sort of superposition of semi-classical states picked on these smooth geometries. Another way to think about it geometrically is that you have a superposition of proper times. For instance, take these two space-times. Imagine the word line that is sitting where this mass is. Depending on whether the mass is there or there, proper time is going to be passing differently, right? When it's closer, it's going to pass a bit slower. If you take the difference of these proper times along this word line, you get the neat way to write the formula for the phase, which is just the proper time difference times the mass. So there is a geometrical interpretation of an effect, whichever way you think about it. Now, that's very nice for, see in our mind what is happening, and for people that already believe that there is such a thing as quantum gravity, this is satisfactory. But given the claim sought after in these experiments to demonstrate that you need to go beyond general relativity or to say that you have the first evidence of quantum spacetime, I don't think it really cuts it. It's too, it sort of comes down to assuming already that there is a quantum theory of gravity to conclude that there is one. You're basically saying, look, whatever this theory is, it's going to have some sort of semi-classical states, coherent states, and then you're going to need a superposition of semi-classical states so that the field gets entangled with degrees of freedom from matter in order for the entanglement to arise. And I totally believe that, but as far as arguments go to say that this empirical data taught you something, it's not very clear. So it would be great if we had some theory-independent line of argument, which I'll say a few words about now. People have tried to do that. The issue has to do with how to model the degrees of freedom of space-time geometry. And if you would try to do it with gravitational waves or with some sort of subsystem locality, like think of subsystems of space-time, you do not get a clear story. Right, so the idea out there about how to make a theory-independent argument for the importance of mediated entanglement is along these lines, that you try to model what is happening as two subsystems, the two masses that are not interacting directly, that are not coupled directly in your Hamiltonian, and to say that the thing in the middle, the mediator, is some sort of degrees of freedom of space-time, and by LOCC arguments, it cannot be a classical variable. Now, I personally do not think that this can work. I'll try to sketch the reasons, although I don't want to make a strong statement that it can never work. I want to make the statement that it's a bit misleading. We should be thinking of something else, but I will come to that. So this is the idea for the no-go theorems that are out there, which is write some piece of mathematics where you have incompatible statements, tick off one of them by experiment, see the entanglement, and then you have to drop at least one of the other two. And the idea is that you would not want to drop locality of interaction, so you will be forced to assume that gravity is not classical. The problem is that the kind of locality of interactions that is being assumed here is actually not so costly to drop because it's the subsystem locality that is quite unfamiliar from quantum field theories and even classical field theories. It's something that is very natural to have if you are doing, if you're thinking about an optical table where you have gates and everything is fine spatially, but it's not a very natural notion to have, to think as fundamental in physics. So I'll go quickly through the slides to get to somehow what I want to tell you. The point here is that a few years back we were trying to understand the role of locality in this kind of experiments, also in the hope of making sense of that kind of argument. And of course, there is locality in this story. If you turn on C, the speed of light, you do have that entanglement is being created space-time locally. It's not an instantaneous thing. For instance, in this example, you would not get entanglement because they are not causally connected, the two masses, while they're in superposition. You can do the analysis in linearized quantum gravity. You find that these phases are actions that are Lorentz invariant, so you can deduce from that they're space-time local. You can do all that. The point is that this does not help you. This sort of retarded propagation is still not going to give you what is this middle thing that you want to call, what is the state space that you want to put here in the middle and run the machine of LOCC. You can show how that notion of locality, subsystem locality, which is basically this one, to assume that evolution decomposes in some tower of boxes where you don't have a box acting non-trivially on both A and B. So in this sense, you can call this a mediator. Yes, it does sort of arise, it does arise from microcausality. If you take a scalar field theory with some approximations, the one that you definitely cannot do away with is the compact support of the masses, which is never going to happen. You never have compact support. And actually, in realistic experimental settings, you will probably have very big overlaps because they would make squeeze states and have them overlapping. And it's going to get worse with gauge. There are these nice arguments here that this notion of mediator is going to be gauge dependent. Roughly, you will have it if you do something like a Lorentz gauge, and you will not have a mediator in this sense if you're working in the Coulomb gauge. So that's not very clean. And like more heuristically, what I think is happening is that we're in a regime where it's not useful to think of radiation. All right. In what sense? That we're talking about the Newtonian regime. It's a completely non-relative regime. These phases that are being created and give rise to entanglement are potentials. And in this regime, what we call radiation is not very well defined, because I'm giving you here an example. In electromagnetism, the transverse part, what you call photons, actually depend non-locally on the source. They become well-behaved notions when you are far away from the source, approximately and exactly at asymptotic infinity. But here we're in the regime where we care about this, essentially. And these things are just going to be behaving non-locally. So I do not feel that the interpretation of this effect in the non-relativistic regime would involve some notion of locality. It's more of a global effect. It's a superposition of spacetimes. You're putting spacetime in superposition everywhere. You're not doing something locally. And another motivation is that I would like to have a package that gives you also the importance for ideas that do not involve subsystems at all, like single system tests where you have a condensate self-interacting and giving you non-Gaussianity, or corrections in some thermodynamic observable. But this is a single system. You wouldn't even know where to begin if you were to try to do an LOCC argument. Okay, good. So I went very fast in this first part because this is what I really want to talk about. So I think that one can make sense of the importance of these experiments by thinking instead of what are called observables in the traditional sense of observables of general relativity, which are invariant functions on the space of solutions. So the space of solutions are the metrics, two forms symmetric, and you have functions or functionals of these things that go to some target space, not specified. It could be some Rn, and they are invariant under diffeomorphisms. In other words, they're functions of the orbits, where the orbits you go by hitting a metric with diffeomorphisms or by making a change of coordinates. All right, so these are things that take as input the entire space-time and give you some number. You can think of them as global in this sense. And I will be talking about something which I call a purely global observable as opposed to global and local. So this is an example of a purely global observable. This is a diffeomorphism invariant thing. I am not saying that is well defined on the entire space of solutions. It's not, but it will be well defined. For instance, for tabletop quantum gravity, you could restrict to asymptotically flat. It's not a problem. And this will be well defined on that. It gives you the mean curvature. You also know this as a Hilbert-Einstein action. Now, there is a famous set of issues in general relativity that is called the problem of observables. And this might seem to pose a problem. I mean, isn't the whole thing dead in the water? And no, it's not a problem. And I will tell you why. Because first of all, this is a very simple regime where we don't need to work with the full generality of general relativity. And the problem of observables, people mean different things with it, but the most serious set of issues has to do with completeness. Not with having observables, but with having a complete observable, a complete characterization of a space-time geometry, which now there is a very sharp formulation of this issue, which tells you that, in fact, it is not possible to have both completeness, a complete observable that discerns space-times, and have them definable in some specific sense. Now, now comes a jump. I personally did not want to go into, I did not want to have these issues that I do not think they are relevant for tabletop quantum gravity. So I wanted to go in a setting where I have full control. And I do have complete observables. There is no problems with infinity at all. It's a completely discrete setting. And see what I could learn. So this is a context of weighted graphs. So having in mind, when I talk about graphs, you can think about applying it to a discrete version of general relativity, like Regge calculus, which we have analyzed, or something like spin networks. You can think of quantum geometry, but it's just a general discrete abstract setting. It's graphs that can have arbitrary weights on them in the reals or in the complex. And instead of diffeomorphisms, you think of permutations. So you think of permutation invariance instead of diffeomorphism invariance, and the analogy goes as follows, is that in order to define a graph, you will put down labels for the nodes, these orange numbers. And this is a completely fiducial, arbitrary thing. So if you change the labels, you should not be changing whatever it is that you're going to call observable. So the observables are the things that are invariant under permutations. There's a passive and an active way to see it. The passive way is the simplest. You just erase the labels and put down new ones. And what remains invariant is the relation between the weights, the capital A, B, C, D, and the alpha, beta, gamma, delta are node colors and edge colors, and for instance here, the fact that between the color B and the color D there is a color gamma on an edge is something that you will find that will remain invariant. So that's an action of Sn on the space of labeled graphs. And if you want, what is happening here more than, I don't know, acting with Sn on a bosonic system is that you're also preserving adjacency. Right? You're preserving the connectivity. All right. So once you put yourself in this setting, there are observables. You realize that, okay, so all the invariants will be global objects. Because you're doing this permutation invariance, it's like diffeomorphisms. If you want, it's really background independence. You do not have something behind the graph to tell you the localization of the graph, like you do not have something behind space-time in general relativity to tell you how to talk about regions of space-time. So these observables, the invariants and the permutations will take in an entire graph. It will give you out some information. And you can do this completely, which means that whatever it is that you might think as a local feature of the graph, for instance, this building next to that and so on, you can encode it in invariants, in global objects. I'll tell you very quickly how this works. It's a very nice construction that you find in a corner of the world of mathematics that think about the graph isomorphism problem. So basically the trick is that you're working with two graphs. One is a graph that you want your observable to eat and give you some number. All right, so you have an observable that is a functional on the space of graphs. You can have any graph here. And you construct each observable from another graph. A multigraph meaning that there is only integers now on the edges. And these integers, what they're going to be are powers of a polynomial. And there is an adjacency information. So the way it works roughly is as follows. It's quite intuitive. You take this graph structure and you hit a bigger graph. And what this observable will do is go search for all the instances of this structure. So let's say that G is this tetrahedron. You will see that you can embed this structure in 4 different ways. Let's say you embed it here, where it's a B, B, B. Then you take the product of them and you raise it to the power that it says here. Here is just 1. So you're going to get a B cubed, which is this thing here. If you go to one of the other 3 edges, you get this A squared times B. Now, if you evaluate this on this tetrahedron or that tetrahedron, notice that these are globally the same. If you would try to do it with just averages, global averages, you would just get the same thing because it's 3 edges that have B and 3 that have A. But they're different geometries. And this thing can see it. It gives you a different value for any value of A and B so long as they're not equal. And so we call these things global and local because they're invariants. There is a group averaging here, which is sort of going around the whole graph to look if this structure exists. But it's also capturing information that you might call local because it has to do with connectivity. So, yes, you can have complete sets of observables on the space of all weighted graphs that are only made of this kind of observables that are created by connected multigraphs, and you're guaranteed there is an algorithm of how to find them, which is guaranteed to end. So they're constructible. They're, of course, the combinatorics explode, right? This is, you do not expect this to go polynomially, this problem, so you're not actually going to write them down unless you have some very huge computer, but you do not have a definability issue. You can be certain about what you're talking about. These kind of observables fully capture all the information that you would like to call as physical. All right, so why am I saying all this stuff? Well, okay, these things have their own interest, but the way it relates to entanglement through gravity, I think, is as follows. Let's go back to the superposition of spacetimes. What is happening here? Well, it's easy to convince yourself that what is happening is that you're putting the distance between the 2 regions in superposition. You take the geodesic between the 2 regions, and you calculate the proper distance, and that thing is changing across the branches. A very simple argument is go and do a different coordinate change on each space-time so that you put the 0 of the coordinates here and the 1 there. And then you sort of disentangle the coordinates and you see that you have a superposition of distance. Now, why am I saying this? Because many people have talked about quantum reference frames before. And essentially, this is what they're talking about. Go to each branch and do something different, what people call quantum controlled. So that's what you would call a quantum coordinate or a quantum diff in the paper with Jeremy, for instance, the paper that we have with Caslav and so on. So, so I'll give you in the next slide a more, a well-defined notion of what this is in the context of permutations. But let me make the following point before I go to that. Right, so notice that something like this, a distance that you have in superposition, is not the kind of observable that I was talking about. That's the kind of thing you have if you've already fixed space-time. And so you know where to tell me to put my 0 and 1 and what is this curve and so on. Observables are things that give you a value for any space-time. You give it an expanding universe, a black hole, something with radiation, whatever, and you get something. There are functions on the entire space of solutions. So what is an observable of the kind I was talking about? Well, this one. So you take you integrate 2 times covariantly, you put some curvature here. Ricci is not going to work because they're going to have 0, but you can put the Kretschmann scalar. And this is a formal way to write covariantly, find the geodesic between the 2 points x and y. So roughly what this is doing, this is some sort of 2-point function that takes all the pairs of points. And if there is curvature, you get a contribution. So when it finds these 2 regions, you will get a contribution. It's going to find the geodesic. It calculates the proper length. So it's a 1-parameter family of observables. If you would plot this against L, you feed it one of the space-times, you calculate it many times for L, and you're going to see a peak at the distance between the 2 regions. So that's a covariant. So that's an invariant way, of capturing the notion of distance. And what's the point? That this thing will have to be quantized if you see entanglement through gravity. This will be an observable of your theory that you cannot have as classical. So what I'm trying to do is formalize this kind of idea. And if you want a main message here, because I also noticed this in the previous talks, if you want to talk about invariance, about observables, that you're sort of, it's very immediate to see that if you do a covariant integration, you get an invariant. But if you're just doing one, you're doing something trivial. You're just capturing local information. If you want to get like the wrinkliness of space-time, you have to go to 2-point functions, 3-point functions, 4-point functions. And if you want, this is what is being modeled with the graphs. You need connectivity information. Okay. And this is the last slide. Or is it? No. Okay, so these are things that we're doing now. What is the next step? You have a good understanding of how these observables work for graphs in the classical case. Then you quantize them. And to cut a long story short, you can define a Hilbert space of graphs where this is basically a Hilbert space per node and per edge. So you have the labeled graphs as a basis that is orthogonal. Then you can define these observables, and then you can do everything invariantly. And you have, as basis of the invariant space, the equal superpositions of the labeled graphs in an orbit. Those are isomorphic. You get a good notion of quantum graph in the sense that you can really talk about density matrices or superpositions of graphs. You have this notion of quantum permutations, which is essentially what they have here in the paper by Markus, Muller, and his group, which is very nice about showing that you can only have fermions of bosons if you demand invariance under quantum permutations. This is basically the notion that they have there, but for graphs, so there is also connectivity. It's not the notion that Ofek was talking about, that's even more subtle, but it's, if you want, a generalization of the idea of doing quantum control transformations appropriate for an invariant setting where you will not be able to do it to split things in a tensor product, because after you symmetrize that, you will no longer be able to talk about specific nodes and so on. And you will we also have a good understanding of the conjugates. We will generally look like that, and the conjugates are those that change the graph. So you have a complete set, a tomographically complete set of observables for quantum states of graphs. And one thing you could do with entanglement through gravity is model the situation simply with a graph, where you have the left-right as one color having two positions, and the other must be the blue, and then you have the distances as the edge colors. You write down a superposition of graphs, and then you can have, we're working on having an invariant notion of entanglement that tells you invariantly that yes, here you are actually entangling space-time with the colors, which can be done using something called a generalized entanglement, which is a generalized notion of reduced state, choosing a subalgebra of the observables I was talking about, and a generalized notion of purity. And okay, I said too many things. I leave you with that. Thank you.
Thanks a lot. We have time for one quick question. In the meantime, Nikos, please prepare for. What questions do we have? Is there a question? Okay. Then, in the interest of time, I would ask Nikos to move on.
Thank you.
Thanks again to Marius. Yeah. Oh. Okay, are you ready?
I think I am. So, slides on pointer. Good.
Okay. Now we have Nikolas Mitrakos, who will present a talk on gravity-induced entanglement. Thanks. The stage is yours.
Thank you, Jan. So I hope you're all excited by the second part of Marius' talk, but this talk has to do with the first part. Let's get right into it. Marius briefly presented GME, and an important part of the discussion around GME is interpreting a positive result from these experiments that should happen in the near future. A big part of the literature aims at understanding and interpreting the results of GME by extrapolating to another regime, specifically to a thought experiment. So for everyone who wasn't here on Monday to see Bob Walt's talk in the previous conference, I will briefly present the thought experiment. We have an Alice and a Bob. Alice has put her particle in a superposition of trajectories, for example, by coupling to a superposition of spin states. Spin up means her mass is on the left, spin down means her mass is on the right. And Alice's protocol is to recombine the two trajectories, and at the end of the recombination, check to see if her spin state is still coherent. In space-like separation from this protocol, there is a Bob who has a particle trapped in his probe, a probe particle trapped, and then he chooses whether or not to release his particle with the goal of, within a time that's, again, space-like separated from the region of Alice's experiment, to measure the position of his particle and gain which path information about Alice. You can think of this as kind of a generalized double-slit experiment when you're on the one side here doing the double-slit experiment and trying to see interference, and you're also in a space-like separated region trying to cheat and measure which slit the particle went through. Now, if you naively analyze this setup by ignoring quantum fluctuations of the mediating field, gravity in this case, then you get into a paradox. The paradox is the following. Imagine that Bob manages to get which path information, And then from quantum mechanics, you expect this to cause decoherence in Alice's particle. But if this were to be the case, then Alice decoheres by something that is happening in space-like separation, so we're breaking causality. On the other hand, you try to reverse this and you try to say that, okay, no matter what Bob does, Alice will remain coherent. But then Bob can acquire wedge path information without causing the coherence in Alice. So we have broken complementarity, we have broken quantum mechanics. Now, the resolution to this paradox involves taking into account the quantum fluctuations of the intermediate field, here gravitons, basically. And the received view that we understand came from these previous papers is that you can make this consistency argument to say that, if we actually manage to do the experiment and Markus sees entanglement in the Newtonian regime, and then we also argue and extrapolate in the relativistic regime that we should have consistency with causality, then we could say that we have seen gravitons. What we did was to give a specific theory-dependent understanding of this thought experiment with a scalar QFT model and see in detail what is happening there. So the QFT model is the following. We still have two masses, A and B. This is the interaction Hamiltonian. They interact with the field in the following way. The coupling is linear, and along each trajectory of each mass, it couples to the field exactly at its position. So we have the two trajectories for Alice's mass, two trajectories for Bob's mass, and they couple linearly to the field. Notice there is a slight difference with what I described before with the papers and the thought experiment, which is that the situation is kind of symmetric here. We don't have a freely falling particle for Bob. We have both of the particles undergoing a splitting and recombination process. But this, however, allows us to write the dynamics for the full system of mass A, mass B, and the field in the following simplified form. Basically, the evolution of the total system breaks into the 4 branches that we have for the masses, and there is no back reaction from the field to the masses, so they stay in their original states. But for each of the 4 possible configurations, meaning left-left, left-right, right-left, or right-right, the field evolves differently. There are many models on this previously in the literature, but our goal was to also try to recover the thought experiment and the paradox within QFT. So we do the setup, we have the two masses undergoing the splitting and recombination, and we ask, what is the final state of the two masses? This is the final state of the two masses. The anti-diagonal terms, x and y, I briefly mentioned because they are not relevant for the thought experiment, but they are related to the phenomenon of entanglement harvesting. So this is the setup again, the two masses undergoing splitting and recombination. And let's take a brief look into the two types of terms that we have. We have the red terms, which are decohering exponentials, just exponential with negative exponents. And we understand them as the quantum fluctuations that pretty much describe what quantized radiation is being produced by the particles because of their interaction with the field. So if I can imagine only having Alice and looking at what her particle is doing, then if I ask at the end of the recombination, how many scalar particles did she produce, gamma alpha will give me exactly the answer. And gamma alpha as a QFT quantity just depends on the anti-commutator of the field. The other type of quantity that we have is the phases, here with blue. And what they describe is retarded propagation. So you can think of Alice sourcing a retarded potential in the scalar field that causally reaches the position of Bob. And this is what gives him access to wedge path information. And we have, for example, for the right branch of Alice, she will source a potential that Bob will be sensitive to. We have in total 4 sources. These are the two phenomena that pretty much describe this whole setup. Again, decohering phases that have to do with particle production and wedge path information carried by retarded potentials. So let's try to recreate the thought experiment. Good. So as you remember, the thought experiment has Alice having created in the far past a superposition of the two states and doing the recombination to check her coherence at the end. In space-like separation, there is a Bob doing the splitting and recombination protocol to try and gain which path information about Alice. What this means is that there is no retarded potential sourced by Bob that reaches Alice. So we have signaling from Alice to Bob, but we don't have signaling from Bob to Alice. So to recreate the paradox, we need to ignore the quantum fluctuations. And there's two ways of doing this, which recover the two sides of the paradox. The first way to ignore quantum fluctuation is to just say, OK, I will by hand put the gammas to 0. I am ignoring all the radiation that is produced. And then I'm asking, what is the final state after this protocol? Alice stays fully coherent, because Bob cannot signal to her. And there is no radiation. We ignored it. And then Bob gains which path information from the retarded potential sourced by Alice. This breaks quantum mechanics and complementarity, because you can see that Alice remains fully coherent while Bob gains which path information. What this means, for example, is that the total state, if you try to look at it for A and B, will have negative eigenvalues. So we indeed have broken quantum mechanics with this approximation. You can also define the visibility of Alice, again, meaning a measure of her coherence, and the distinguishability of Bob, and it will generically be more than 1, which means that you have gained for free which path information. The other side of the paradox is to do the ignoring the quantum fluctuations procedure in a different way. Basically here, we're going to be doing a stationary phase approximation of the dynamics for the field. So we're going to think of the field as being classical and only evolving through the classical equations of motion. Now, there is previous work on this that Marius also mentioned. And what happens here is that quantum mechanics is OK, because you can say that you still have only as a phenomenon the retarded potential sourced by Alice reaching Bob, but now Alice also has access to them in a way that saves complementarity. So if Bob gains which path information, Alice will decohere. But again, we're recreating the paradox exactly because you can think, aha, what if Bob wasn't there to measure and gain which path information? Then Alice would be coherent. So Alice can tell apart the two possibilities of Bob measuring or Bob not measuring, which leads to superluminant signaling. Note that in both sides of the paradox, I have talked about retarded potentials carrying the information from Alice to Bob. The resolution of the paradox in full QFT, which is also looked at in the previous literature, has to do with the fact that you have exactly the gammas, the produced radiation from Alice and actually from Bob in this model, that give you the decoherence that you need to be OK with complementarity. And the which path information is still fully carried over from Alice to Bob by the retarded phases. So in the full QFT description, actually it is the uncertainty principle that saves us and doesn't cause a paradox, because the decoherence that you will have from the quantum fluctuations, from producing radiation, will for sure be larger than what which path information Bob can have access to. So what does this mean for GME? We want to tweak the received view in the following two ways. First, that we think the argument holds. So the papers are not doing anything wrong. But this consistency argument and extrapolating to it, we believe requires a further ingredient. It requires you to also empirically add as an ingredient retarded entanglement. Because as you saw, we created the paradox, but it was always retarded propagation carrying the which path information. So what we think is that if we extrapolate, if we have as an input empirically retarded entanglement, which you can do, for example, by proposals that are an experimental setup, maybe a generation away from just tabletop Newtonian entanglement, then you could extrapolate to the consistency argument in the relativistic regime and say that there should be quantum fluctuations of the field. But again, this is an empirical input that is a step further from just seeing Newtonian entanglement. You would also have to see retardation corrections. The second part that we would like to tweak the received view with is that it is exactly retarded potentials that carry the which path information, at least for our model, and that the quantum fluctuations have different effect compared to them. They are relevant for the decoherence part of the setup. With this, I thank you.
Sorry. What questions do we have? Bob, please.
Microphone, I think, right? Yeah, so I think I agree with everything that you said. I mean, if you look at the wording in our papers, we don't say implies gravitons. It's this suggests that Newtonian entanglement, et cetera, and supports the view. But the main point is, I mean, the retarded potentials, you have the retarded potentials there, but they can, you're doing the scalar case, of course, they can be interpreted as scalar, radiation of the scalars, not Newtonian-like potentials. I mean, that's one of the main points of our, my paper with Dane and Gotham, that the blue arrows can be, when received by Bob, and you could see this by choosing a different time slicing, be viewed as part of the radiation that Alice is emitting. I mean, there is not a clean red and blue distinction between Newtonian-like fields and radiation in terms of what Alice is creating. I mean, I completely agree with all your formulas, but that was, well, I think I more than made the minor comment that I wanted to make.
No, thank you for the comment. And it is true that we did not ask intermediate questions, and we're also not asking, can Bob differentiate between receiving retarded potentials or receiving gravitons? This is not a question that we posed, and it is answered in your paper. Maybe the only quick comment that I could also use to answer is that the way we are saying that you can only differentiate between these two terms is because we're calling the blue arrows classical in the sense that they do not depend on the quantum state that you put for the field beforehand, whereas the red terms do depend on the quantum state that you use for the field. So if I use a different state for the vacuum, for example, in the beginning, it would be the red terms that change and not the blue ones. And again, this is not a strict de facto argument. It is just, and we're not asking intermediate questions. It is just that the thing that we noticed is these are different field functions. One of them is the anticommutator, one of them is a commutator, and of course in QFT everything is going to be quantum. For sure, you will also be able to express both of them as integrals in the Fourier space over all modes, which you should also be able to call gravitons. But we're trying to do this differentiation mainly to note that it is the retardation that is an empirical input in the setup. But thank you.
Then let's thank Nikos again. Alberto, please.
Okay.
Just if you also can use the slides, if you can see it. No? Ah, yeah.
Okay.
Then we have next Alberto Spalvieri, who will talk about local operations and also in the context of field-mediated entanglement. Please, the stage is yours.
Hello. Thank you, everyone. Today I will talk to you about a work I've done together with Sébastien Garmier and Flaminia Giacomini when I was at ATH during my master thesis. And it's now also a preprint on arXiv, if you're interested. But let's get rid of this very messy first slide and start with two simple concepts everyone of us is very experienced with in quantum mechanics and quantum informations, which are local operations and entanglement. So we know in quantum mechanics we can take two quantum systems and associate Hilbert spaces with each of them. And then the theory tells us we can combine them simply by doing a tensor product of the two. And this is what we usually refer to as the local tensor product structure of our bipartite system. And this structure allows us straightforwardly to define a nature notion of locality, subsystem locality. The local operations will be defined by those operators that act trivially on one system and only on the system we are interested in. So these will be the local operations for A and B, respectively. Also, this decomposition allows us to define entanglement straightforwardly, very clearly, because now entangled state will be the ones that cannot be written as a decomposition on as a separable state on the two subsystems. So now, as was also mentioned in previous talks by Marius, and this structure is not always true. If you are interested in looking at gauge theories, this structure can be put to stress because, for example, let's take electromagnetism. In classical electromagnetism, we have a gauge constraint, which is given by the Gauss law, which restricts the value of the electric field at different points in space. Once we quantize it, this becomes an operator equation, which now restricts instead the set of states, which can be considered as physical. So if we now take the Hilbert space before requiring this constraint, this can be naively written as a local tensor product structure of Hilbert spaces of the field at each point of space. But now, if we require the constraint to be true, since we have this divergence appearing now in the constraint, which is a derivative acting on different fields at points of space, this will connect all these different Hilbert spaces, and thus we will not have our standard local tensor product structure. And this, of course, puts to stress a bit the definition of local operations and entanglement we had already. And why this is interesting? Because these notions are very useful in defining tools in quantum information theory, for example, LOCC theorem, which is used and are used in analyzing the nature of gravitational field. And of course, since we know that ultimately the gravity is a gauge theory, and we would like maybe to describe the field-mediated entanglement experiments in gravity, for example, linearized quantum gravity, this notion of local operations and entanglement could be interesting to analyze. And what we did is try to start from a very naive approach, and we begin with a simple toy model. We have this lattice gauge theory where, not as in the usual lattice gauge theories, we put field degrees of freedom on the sides instead of the edges. And this will turn to be a very nice simplification in the calculations. And we construct this toy model to be a full analog of electromagnetism. So we take this Lagrangian to be a Lagrangian of a gauge theory that has position and momenta corresponding to the potential and electric field. And then this Lagrangian will result in a secondary constraint, which is analogous to the Gauss law, where now these derivatives are discrete derivatives, which are constructed as differences across the lattice. So very easy to visualize. And then we can also find the gauge invariant quantities that commute with the constraint, which correspond to the discrete version of the magnetic field. And as well, we can find the Hamiltonian to be analogous as well. Then we can also add matter to this model. We just put a discrete function of matter on the lattice. And with this addition, we just have to modify the constraint if we consider static sources, as it will be the case for field-mediated entanglement. So we just need to modify the constraint as it's done normally in electromagnetism. Now we quantize this model, we impose the standard canonical commutation relation, and we impose the operator constraint, which now it's even more clearly breaking the local tensor product structure, because these discrete derivatives are now just differences of the field on the lattice, and so these clearly cannot be written as a local tensor product of Hilbert spaces of the field at each site. We also model a very simple quantum matter, which is given just by qubits at each site, where 0 represents no particle and 1 a particle. And with this model, the density operator is just checking if there is a particle or not in a site. And with this, we must modify the constraint, like this, and just add the operator. And having now this construction, we can find a generic state of the matter plus the field in the ground state. And we can compute now in this very simple model, thanks to having the fields on the site and the simplicity of the model, we can compute explicitly the ground state, which is the discrete analog of what was found for electromagnetism. And so it's a Gaussian which is based on the classical configuration of the sources. And now in this simple model for matter, we can only look at superposition of classical sources. And so we will have this entangled state where now the field and matter are always coupled. And this will be responsible also for the generation of entanglement in the field-mediated entanglement. And now we look at how to define our generalized notions of locality. Let's see. We take this lattice and we define a region A, which is the region where we want to construct our local algebra. And we want this local algebra to contain all the operators that are accessible to an agent living in this region. For sure, we need to require these operators to be gauge invariant, and so to commute with the constraint, which is now the modified constraint with the source. And so we can for sure pick already the momenta operator, because we know that these are all commuting automatically with the constraint, since it's depending only on them. And so we decide to include all the operators acting on the sites contained in the region. Then we need to find some quantities that are gauge invariant combinations of the position operators. And these are exactly the magnetic field operators, which now we can represent with this graphical notation. And so these are both magnetic field and constraints can be seen as crosses on the lattice. And so this simplified a lot the computation and construction of these algebras. And we decide now we have some freedom in what to include in our local algebra. We decide to include only the crosses, the magnetic fields that are fully contained inside the region. And so not the crosses that would cut the boundaries. So now we can use some results that were already found in other gauge theories constructions, and we can find a decomposition for these local algebras, which result in this block diagonal structure. So where we have now that in each term of this sum, direct sum, we have the standard local operations acting on A and the rest. And these also induce a corresponding decomposition on the physical Hilbert space. This is done, as I said, through a procedure which involves diagonalizing the constraint of this local algebra and then imposing the center and then imposing the constraint, the full constraint. And with this procedure, we can also see what do this K label. And this K label essentially truncated constraints close to the border, which we call edge terms, and are physically represented by the orthogonal component to the boundary of the electric field. And now that we have this decomposition, we can see how this local algebra acts on the physical Hilbert space. Now, we choose, our conclusion would be that this is the local operations, generalized notion of local operations we want in this simple toy model. This is because we know that, okay, first, they act as standard local operation in each term of the sum. And so if an agent in region A would go close to the border and measure actively the edge terms and make the whole state collapse to just one of the sectors, she will just retrain the same local operations as we defined before. And furthermore, these local algebras act block diagonally on the physical Hilbert space. And so they cannot mix the different terms of the sum, making these superselection sectors. And thus, an agent who has access only to the local algebra A, which is in region A, cannot measure coherencies in these sectors, but only mixed state. And thus, the only accessible entanglement operationally is the one which is well defined in each of these tensor products in each of the terms of the sum. And so we also retrieved an operational notion of entanglement that can be measured by these local operations. So now we can look at how this translates to the field-mediated entanglement example. So we take the three regions now, region A, B, and the rest. And now these are taken far enough apart so that the boundaries do not touch and there are no boundary effects. And then we can take now the physical Hilbert space to be decomposed in this way, where now we have a third term. We are only interested, of course, in the A-B parts, since we want to measure entanglement of sources located in A and B. So we put one source in region A and one in region B. And then we want to see how to actually build the superposition of these sources. And this can be computed explicitly in this very simple lattice model. And this will be given by these unitaries, which cannot act only on the sources, of course, because moving only the source on this lattice would not fulfill the physical constraint anymore. So these unitaries will be dressed unitaries that act also on the field, as one would expect. But remarkably, they belong to the local algebras as we define them. They do not change the state instantaneously, the state of the field across the whole lattice. And of course, then there will be some evolution of the field that includes relaxation and then mediation of the interaction. And this is what we can identify as the field evolution and communication. And so now we have, it looks like we have retrieved some notion of both locality and communication. And if we see now at this term in each of the superselection sector, we also have the standard local tensor product structure. And the operational notion of entanglement. So we can essentially extend the validity of the LOCC theorem to some sort of extended LOCC notion, where we have now that local operation act block diagonally, and so the only entanglement that can be retrieved is the one between HKA and HKB in each of the sectors. And so LOCC can be implemented independently in each of these K sectors. So if entanglement is measured in the end, one must conclude that field is non-classical. Of course, here we constructed the model to be a quantum gauge model. So we can indeed compute that the field is non-classical, and we can compute explicitly the entanglement. And this will be given by the interaction of the field and matter, as we saw in the previous ground state. And so what we showed is that LOCC can be extended, at least in this very simple toy model. And also this I didn't show you, but we can, thanks to the simplicity of this lattice gauge theory, we can actually see graphically how these local operations act on the lattice, and we can compute explicitly the operation that creates the source superposition in the lab, at least its counterpart in the gauge theory. Of course, it would be nice to extend this to more general theories. As we constructed the toy model to be fully analogous to electromagnetism, we can show that this indeed goes into its continuum limit. It goes to two-dimensional quantum electrodynamics. But of course, problems will arise when considering local algebras. And so this is work that must be still done in the future. So thank you all, and if you have any questions.
Thank you, Alberto. What questions do we have? Marius, please.
So this was a very nice talk. Thank you. Interesting. So I know the paper by Eugenio and Pietro, but okay, sort of to tease you. You said you were gonna get rid of the tensor product, but you didn't. You just have a sum of tensor products. So
yeah. In the end, it's not really getting rid of them. In the end, you just show that what you first thought was not having any structure, because you have the gauge constraint. Instead, due to the specific form of the constraint, which was just just a bipart, like a derivative, you can retrieve some sort of locality. Let's say.
But let me push you a bit. Let's say the two masses have an overlap. Then will you have that?
Yeah,
or not?
In this case, it will not. You will not have necessarily this decomposition, because the masses here are also very simple modeled. They are just dots. You can have more than in a certain region, but I think that what you're actually implying is that the region then have some overlap.
There is
also
still spatial localization. You get I think you. It's very nice what you're doing, because you're seeing how to deal with constrained systems, but there is still somewhere hidden space-time localization, I think.
Yeah, there is the assumption that when you look at the field-mediated entanglement, you always take the regions to be enough far apart, which means just don't caring about any interception between the algebras. This is an assumption you have to require, otherwise you don't get this very nice decomposition. Yes. But it's interesting to see if there is more in that direction.
Thank you.
Thank you.
That closes the second section of today's event. We will have the third section so we shifted by 10 minutes to start at 4:10. And it will commence with a career development talk, so especially for younger researchers or students this will be of interest, and then more further scientific talks will follow. So with that, please have a coffee or any rest, and see you in a bit.
Hello, everyone. Welcome to the third section of our conference day. So the first talk will be our director, Markus Aspelmeyer, to give us the career development talk. Markus, stage is yours.
Thank you very much, Lin-Qing. Thanks, everyone, for being here to our, what is it now, second or third edition of the Vienna hosting RQI. I was asked to give IQOQI's perspective on career development in essentially fundamentals of quantum physics, which is definitely a demanding topic. I was also asked to briefly say something about our research. I will keep that only to 2 slides, because afterwards you will have a wonderful presentation of Peter Asenbaum, who will present his experiments, and I think that is at least as exciting as I could say things about. So what is our group doing? Our current activities explore the boundaries of quantum physics and gravity in experiments. This is a picture that was taken at the Einstein house in Kaputz. This was this is a result of something that the city of Berlin wanted to gift a house to Albert Einstein to his 50th birthday. Bureaucracy prevented that from happening, and then 2 years later they actually bought the thing themselves. And it's a fantastic venue to go there and see. It's done by an architect and so on. So why are we doing that? Our ambition in the group is we want to create quantum sources of gravity in the lab. Let's say the theoretical motivation you already heard in several talks today. And our goal is essentially, sort of paraphrasing Kissinger, we want to take both gravity and quantum experiments to where they have never been before. So each of our experiments actually wants to get them out of the comfort zone and do the next steps. How do we do that? We focus on 2 fronts. In the quantum regime, we use quantum control techniques, develop new quantum control techniques to be able to engineer quantum states of motion of more and more massive solids, make them larger, make them more massive, such that eventually they can be used as sources of a gravitational field that can be measured in experiments. On the gravity side, of course, we also need to learn how to measure gravity for such small objects, and this is why we have independently also experimental approaches to make better and better measurements of gravity at smaller and smaller scales with respect to mass and distance. All of that is a collaboration between theory and experiment, and now I'm sort of fading already towards IQOQI, as you can see here. So basically, both sides have to come along, and I will say something about where this picture was taken in a second. So that's what we're doing. We're trying to combine quantum and gravity, basically coming from those 2 sides, from a bottom-up approach, from the quantum side, a top-down approach, from the gravity side, and we hope that eventually those 2 domains will merge. And again, I think you will hear from Peter Asenbaum how his group is actually tackling exactly this interface in new experiments. Now, coming to the IQOQI itself. So here at the Institute, we try to live really this collaboration between between theory and experiment. Our institute is one out of 27 research institutes that are run by the Austrian Academy of Sciences. So this is a non-university research facilities with a committee separate budget from the universities. We are also not giving out PhDs. So these are things, all the students that we have are also students at one of the universities here in Vienna and get their degrees from them. Although our PIs actually can and do teach in particular here at the University of Vienna. The research institutes are across all the sciences, so we have institutes in physical sciences, in the life sciences and humanities. we just have recently opened a new institute of the Academy with a research focus on artificial intelligence that is co-sponsored actually by a huge pharmaceutical company, and so you can see where the expectations are to drive that research forward. Here at IQOQI Vienna, we focus on the foundations of quantum physics with specifically aspects in gravitational quantum physics, quantum aspects of space, time, and measurement. As an institute, our mission is constantly to strengthen and continue to build a internationally visible center for basic research. So really for the foundation of quantum physics, this is something that is rare on an international scale, and we try to sort of reinvent ourselves on a regular basis by continuing to ask new questions and, as we say here, challenge our current wisdom at the forefront of quantum science. So I would say this is the ambition that we have. This is what we try to achieve with all the people working here. And I said that before, we really try to have a combination of theory and experiment under one roof. We want to be one umbrella, and with this combination actually create really a worldwide unique environment and setting for the foundations of quantum physics. The institute itself was founded in 2003. Originally, it was one institute at two locations. The one was in Innsbruck with the founding directors Rainer Blatt, Hans Briegel, Rudi Grimm, and Peter Zoller, and one in Vienna with Anton Zeiling as the founding director. The location here is a very interesting one. I don't know if you have the chance to look around. So this is the historic site of the Institut für Radiumforschung. This is really very, it was the first privately funded research institute in Europe that basically started here with the focus on radium. We have by now 4 Nobel Prizes attached to the research being done in that house, starting with Hevesy for the radioactive tracer method that was developed here, and up to Anton Zeilinger's recent prize for his quantum entanglement research. Now, how do we fill our house? As you can see, we are right now on the order of 70 scientists in 9 research groups, along with typically 40 guest researchers from the University of Vienna and from all over the world. We run on a significant amount of third-party money, and we cherish, of course, our collaborations with partners all around the world. We have 7 laboratories that are distributed here in the building, and we have also 2 additional laboratories, sort of large-scale infrastructure. One is the Hedy Lamarr Quantum Telescope, where the basics of quantum communications are being tested. It's up on the roof, so if you haven't done so, it's always a nice visit. And then we have another facility that we are working in. This is the so-called Konrad Observatory that's 70 miles southwest of Vienna, so 1.5-hour drive where we can operate in an extremely isolated environment, our gravity experiments far away from all the distractions and disturbances of the Vienna City Lab. The institute itself, and the heart of, I think, every institute, of course, is the people. What you can see here is the progression of IQOQI research groups starting in 2003, 2004, and with Anton Zeilinger as the founding director. Then Caslav Brukner joined shortly after that. And over the many years following, several groups followed at IQOQI, and also some of them left to other endeavors. So, for example, Rupert Ursin, he founded his own company, which seems to be doing quite well. And I'm still waiting for the, anonymous check to IQOQI at some point to further fund us for the next 15 years. But also, I think it's also historically correct to say that the idea of a junior group in the Austrian academic system, so which is basically has grown over the last 20 years as tenure track groups and so on, was really established at the IQOQI Vienna. Anton Zeilinger was the first one within the Academy of Sciences system to actually pursue this idea of having junior research groups and giving young people the opportunity to pursue their own research here at IQOQI in this ecosystem. And I actually was lucky enough to have been the first one to benefit from that idea. And we try to sort of repeat that ever since in the hope that the next generation does even better. And I think if you see here below this sort of the trajectory of the junior groups, this idea also became a success here at IQOQI as a career maker for the next generation. So I certainly can say that for me this was the case. And I think I can safely say I personally owe my career to my early days at IQOQI and the opportunities I was given here. And now we have then follow-up groups. We had here Emil Broukal, Konstantin Budroni, Jelena Gorjanova. They have found positions all over Europe. Markus Huber has recently become professor at TU Wien and is now director of the Atom Institute at TU Wien. And now the fresh generation that we have here with various Christodoulos, Esteban Castro-Ruiz and Peter Asenbaum, they are sort of the new beacons of hope. And as you will see in the next talk, Peter is on a fantastic track doing so. We have recently established, and I just put it here on the right, a new concept. We have been launching the IQOQI Quantum Technology Unit that is led by Michael Trubke to actually provide research expertise in microfab, integrated optics, quantum sensing, and so on, and sort of take all the foundational research that is done in the research group to the next level and help also spin them out and provide what we are doing as a sort of foundation for the next generation of quantum technologies. Now, what about the career opportunities that people can have here at IQOQI and the Vienna, let's say, ecosystem in general? As a general rule, I have to say we always welcome applications, right? From young and experienced researchers, so all age groups. The only thing that is a necessary precondition, you have to share the enthusiasm and curiosity about exploring the foundations of physics. With at least this is the sort of once you sort of fulfill that requirement, just be free to apply. So for master and PhD candidates, they typically apply to the groups directly. So you just find your PI that you think does interesting research, you write them an email. What you can also do is you can apply via the PhD programs at the, for example, Faculty of Physics. There's the Vienna Doctoral School of Physics, the VDSP. There is the Vienna Center for Quantum Science and Technology. This is an umbrella institution for all the quantum institutes in the Vienna realm. So the university, the IQOQI, the TU Wien, and the IST Austria in Klosterneuburg. They also have their own PhD programs, IST, but the VCQ actually has an additional round of PhD applications. So you have many entry points from either the formal PhD application rounds of those institutions or those umbrella institutions, or you write directly to the groups. We have, since 2.5 years now, the Austria-wide Cluster of Excellence, Quanta, Quantum Science Austria. You can also directly go to the webpage there, and they also have, in their news section, they provide you with information of all the possible application opportunities that are open at the moment. Those PhD positions are fully funded. So once you get a yes, once you get an offer from a group, this is something that will finance you till the end of the PhD. And on top of all of that, there are, of course, also fellowship opportunities. The Austrian Academy of Sciences offers doctoral fellowships. The University of Vienna offers doctoral fellowships. So these are things that pop up every now and then. And we always actively encourage people to apply for those and to get additional, let's say, how do you say, excellence credits that they can also use for their CV. And it's also, of course, a matter of visibility of IQOQI when young researchers get such fellowships. On the postdoc level, the same thing holds. If, as a postdoc, you're interested in doing research with us or in Vienna, directly contact the groups. And also here we have several fellowship opportunities that come along with that. There are, of course, the Marie Curie fellowships funded by the EU. They actually have quite some advanced preparation time. So whoever is listening right now and is interested, the next call closes in September. So if this is something you're interested in, now would be the time to reach out and start thinking about writing such an application where IQOQI can serve as a host, or let's say the groups of IQOQI, the individual PI groups can serve as a host. We also have, again, at our excellence cluster, there are not continuously, but focused rounds for fellowships. It depends on the time of year. We had 2 fellowship rounds already. One was also targeted to female scientists. So here I recommend check out the Cluster of Excellence homepage. You will always have the latest opportunities being announced there. The Austrian Science Fund, the FWF, also has different programs. The ESPRIT program is a more or less new program that provides funding both for the salary of a postdoc, but also for additional research money to really follow a very specific project where the idea is that the postdoc really is the lead PI on that project idea, as it should be anyway. So this is also something I should say. So we always try to actually grant ownership to the project's ideas, be it in theory and experiment. So we want to work with you, and this is why it's important that you follow your projects and get the support here. We also have at the Gravity Quantum Interface a research network together with the University of Vienna. It's called TOURIS, and we are offering visiting fellowships here for younger research colleagues and for senior research colleagues, from starting at a few weeks up to a couple of months. So if this is something that interests you, just reach out either directly to the Institute or also via the TOURIS homepage. We also, I mentioned that already, we are hosting independent research groups. And I should say a little bit to the idea behind that. We basically model those independent research groups following the lines of the Max Planck Society, or introduced the Max Planck junior groups as non-tenure track groups. So these are 5-year positions at the institute without a tenure option, and the idea is that what you're given is the opportunity to work here at IQOQI with us and in the Vienna quantum environment. And the expectation is that after successfully pushing your group and completing your experiments or your theoretical projects, the group leaders usually should receive tenure track or permanent position offers at the end of their contract period. And so far, this has been the case with our junior group leaders. At the moment, also this should be said very clearly, we do have no openings at present. As you have seen, we have 3 junior groups at the moment that we are hosting. You have seen the capacity of the institute. We are sort of full at the moment, but that doesn't mean that there will not be openings in the future. So if you are interested, then please contact directly IQOQI leadership, in that case Caslav Brukner and or myself. And of course there are other opportunities for independent researchers. There are non-tenure track options through being hosted at one of the institutions here in Vienna. So for example, if you get an ERC grant or an Astra award of the Austrian Science Fund, I promise you there will be a very large conditional probability that you will get a hosting offer from one of the institutions here in Vienna. Some of them even offer a tenure track position along with that. That depends on the institution. I know for fact Faculty of Physics at the University of Vienna is not doing that. The TU Wien has been doing that. So this is basically a question of resources at the time when these negotiations take place. And of course, always keep an eye open for tenure track positions through faculty openings here at the institutions in the Vienna landscape. I think this is what I had to say. Just summarizing, I think here at the IQOQI Vienna, everyone is welcome. We really enjoy working with you and amongst each other. And I would like to state here one more time our vision and mission of the Institute. We want to be and try to be a center for the fundamental research where we can continuously challenge our current wisdom at the forefront of quantum science. And don't forget, Vienna has a fantastic overall ecosystem. We have in this one location, we have 4 different institutions. We have the University of Vienna, the Academy of Sciences, we have the TU Wien and the IST Austria. We have PhD programs in all of those, sometimes together, as I already described. And only since recently, we have the Austrian-wide quantum cluster of excellence, where in Innsbruck, Linz, and Vienna, basically the quantum science community is getting together. It is I would say, community of excellence, as you can see. I think the 32 ESC grants have already grown by now to another 36 because the numbers are 2 years old. And we have, if you look all over Austria, at least 60 PIs working on quantum research, at least a third of them really with a focus on the foundations of quantum science. So it's safe to say if you're interested in learning about quantum science and quantum foundations, Austria is a great place to be, and I think there are many different opportunities. I think the one advice I can give to everyone, particular out there listening, just be proactive. Okay, if you're interested, don't wait for the calls to happen. Proactively approach the groups. I think there is enough opportunities here. Thank you very much.
Thank you, Markus, for the wonderful introduction. Now we take questions. Are there online questions? Okay.
Very good.
Good. Yeah. Our next speaker is Peter Asenbaum. He will tell us about the experimental aspect of gravity-mediating entanglement.
Achso, jetzt mein Computer gebraucht. Was? Achso. Ups. Bin online. Bitte sehr.
Yeah, Markus, I really liked your IQOQI logo with the Nobel Prize, and it clearly suggests that there's one Nobel Prize missing on the other side, right?
It can host at least 4, right? And 1 in the middle.
No, but it's an I, right? There's only 1 dot. So I think 2 is enough. Okay, so this schematic here shows kind of the dream of the experimental physicist here in IQOQI and at a lot of other places, namely to study the interaction between 2 massive objects in quantum states. So here depicted we have 2 delocalized objects and they're close to each other. So this is kind of the experiment we want to do. And the important point is that you need to have 2 things in quantum states. Okay, so as a quick introduction, I will talk about gravitational measurements with quantum states and about the parameter, so kind of what is an important parameter for quantum states, it's K. So what is K? In an atom interferometer, what you do with single atoms, you shoot lasers at them, and what happens if you tune the frequency correctly in respect to the velocity of the atom, what happens is it gets reflected. So you can make a Bragg beam splitter. And the amount of momentum you transfer in such a beam splitter is h bar k, where k is just the wave vector of the laser light. So there's really a direct relation between what you do to the quantum state and kind of what phase is imprinted in it. So the k I usually mean when in my next slide is really the phase gradient imprinted on your quantum system. And if you think about just a standard mirror and you shoot with a laser at it, you can get a very large effective k, so not just from a single photon but from many. So for instance, for LIGO, you can say it has a k of around 10 to the 20. Okay, so what does k mean? It's basically the momentum uncertainty, but it's in nice units, namely 1 over length scale. And the important point, it's really an uncertainty. It's not just the overall momentum, but the momentum uncertainty. So if you have such an atom interferometer, you split it up in different paths and you recombine them. And during this sequence of pulses, what happens is that you have 2 paths and they will separate over time. And the typical number for this separation is the wave packet separation, which is given by h bar k over m times time. So the k kind of tells you how large a quantum system will grow, depending on its mass and how much time you have. So that is k, that's important to remember. Now let's look at kind of the state of the art. What can you do with single quantum systems? What kind of gravitational measurements can you do? So you can do acceleration measurements, for instance, equivalence principle tests, where you measure gravitational acceleration. Or the other thing you can do is you can measure gravitational energy. You have large quantum states and interact with a classical source mass. Okay, and if you take this experiments with single quantum states, you can make additional assumptions and say something about different models of gravity. So for instance, if you have quantum reference frame transformations, if they hold, then you can make some inferences about gravity just from a single quantum state. Okay, and the important point I would like to stress here is that so with additional assumptions you can obviously say a lot more than without the additional assumptions. But what is kind of an important point is that these additional assumptions you do on single quantum state systems are a lot stronger than what you hopefully do for the entanglement experiments I will talk about later, right? So the entanglement experiments are a lot harder. So in the end, you want to have less stringent assumptions for these experiments. So this is kind of I feel it's important for theorists to keep in mind that the assumptions should be less than what you have for single quantum states. And the other message is with single quantum states, especially with atoms, we can do basically anything. So if you have very good ideas, those are fairly easy to implement. Okay. of course, this is not enough, so why do we want more? Why do we want to have two objects in quantum states interacting with each other gravitationally? So for me, and probably for many other experimentalists, the main motivation is that this would really be an experiment that goes beyond GR. So it's kind of the big motivation to make an experiment which is qualitatively no longer compatible with GR. So what do you need to do that? So you need to have a delocalized source mass. And typically, when you look at the quantum systems we have, this is a hard thing to do. So of course, it's not enough to have a delocalized source mass, but it needs also, the mass needs to be large enough so that you can actually measure it. So that means you need to have a quantum state which is sensitive enough and a source mass which is heavy enough, and in the end you will get an interaction which can create entanglement. Okay, so what quantum systems do we have? We have single atoms. They are, as you can imagine, they are too light to do this kind of experiments, and the macroscopic systems we have so far are not very delocalized or not very quantum. They don't have long coherence times, and their wave packet separation is not very large. And so when you look at quantum systems, they typically follow a kind of a trend. The higher the mass, the smaller the quantum state. So this is kind of the problem we are facing. Yeah, so since this is a tough experiment, it's important to look at the scaling properties of the effects you want to measure. So if you look at two quantum states, two path superposition states, so one interferometer up here and one interferometer down here, where the particle is in a superposition between two states, you can easily measure what is the phase shift along the one interferometer given the position of the other one. And if you look at the difference between the two arms of the other one, you get four terms, which is very easy to do. So what appears in these terms, you have the product of the masses, you have the distance r, and also you have the wave packet separation of each of those states. Okay, so and this term here, phi GE, this is what you want to observe in the end. So you want this to be 1, right? So this is a phase shift, and if a phase shift is order 1, then you can do it in a single shot. So now you can look for different masses and different wave packet separation. This is very easy to do. So if you have large wave packet separations, which also means low masses, what you will see is you get the term that looks like this. So it just depends on the product of the masses and 1 over the distance. And when you put in the numbers of atoms, obviously this will be a very small number. And in order to combat that, you could have some high mass uncertainty states, but this is to really get to 1, this is completely unfeasible. So so kind of the next step would be, instead of having two quantum states of atoms, you can take one quantum state of atoms and one of a macroscopic object. So if you have a macroscopic object, then the mass is very large, wave packet separation is very small, so the phase shift in the end will look like this, where it now only depends on the mass of the weak particle, on the small particle, and suddenly you have a k in there. As mentioned before, this is the important parameter for these interferometers. And if you put in numbers here, if you take again the mass of an atom, it means that the k needs to be extremely large, kind of to compensate for the small mass of the atom, which again is very unfeasible, or it's just unfeasible. Okay, so basically the only solution you have is you take two massive objects. Why is this kind of a good solution? Is because now you're independent of the mass, but you have a k squared in there. So k, obviously, if you do a good job, like LIGO does, this can be a very large number. And with these two large numbers, it's only very hard to get this to be equal to 1. Okay, so the point I'm stressing here, if you look at two path superpositions, you need to have two massive objects. Okay, so as a next step, you can look at kind of noise. So when you do experiments, you always have noise, and you don't want to be too sensitive to them. So if you look at two-path superpositions, where basically the wave packet separation is a lot larger than the distance, then you have additional acceleration sensitivity that you not really like or need. So this is bad because it scales as wave packet separation over the distance, extra kind of. Yeah, in case of these hybrid systems, you also have an additional factor which gives you unnecessary acceleration sensitivity. And in the most visible case, you just have the normal acceleration sensitivity, which is linear in k. So basically, every acceleration a creates a phase shift, which is k times a times interferometer times squared. Okay, so this easy calculation is done with two-path quantum superpositions, but in this region where the masses are high, you get the same scaling for Gaussian states, which can also be found in this paper here. Yeah, so for this small quantum state regime, which is the one over here, it makes not an obvious difference whether you use Gaussian states or two-path superposition states. Okay, so what is the biggest fundamental problem, I would say, in doing experiments with macroscopic objects, quantum experiments? It's thermal noise. Yeah, so here again you have the phase shift for entanglement. There's a certain limitation on the minimal distance between the two objects, which is given by Casimir interactions. So typically, once you go below 100 micrometers in distance, Casimir will be a lot larger than gravity. So this is kind of a region to avoid. And if you now look at thermal noise, right? So if you have, so this is for a specific kind of dampening, but if I have thermal noise, it's a forced noise, right? And what it means is that the acceleration from this forced noise, they get lower the more massive your object is. So if you look at thermal noise, it's obviously very advantageous to have a high mass particle. However, when you make your particle too large, obviously the radius or the distance between the two objects has to grow with it. And if the particles get a lot larger than the minimal distance, the scaling of the entanglement phase shift over thermal noise basically stays constant. So that means basically there's no big benefit, at least, to scaling up the particle mass to larger and larger sizes. And in particular, what you have to do, if you scale up the mass, you have to scale the k with it, right? Because the distance gets bigger, so you need to make k bigger and bigger to compensate for that. So the point I'm trying to make is, in principle, you have room to grow with k, right? So if you look at macroscopic objects like LIGO mirrors, you have a k of 20. So yeah, from what I will show you afterwards, there's a little bit room to grow. However, things don't really get easier. If you look at the expansion of your quantum state during your interferometer sequence, stays constant, because it's just the wave packet separation measured by k, which then h by k squared over m, which stays constant. So the one number that kind of immediately jumps out to you why these kind of experiments are very hard is this quantum state expansion ratio. So how big does the quantum state need to be during your experiment compared to what your measuring resolution is? Yeah, so basically the whole problem is pretty much, is pretty well confined from all angles, so there's not really an easy way out. Okay, so now back to two-path quantum superposition states. The question is, what is the better state to use, right? So I've told you before that the scaling is fairly similar for Gaussian states or for two-path superposition states. And Yeah, so in these original proposals by Malletto-Vetral and Bose et al., they proposed to use kind of spins in diamonds, in large quantum states, basically, and let them interact. And I would argue that obviously this is not the best choice of a system. And why is that? So basically, in macroscopic objects, having good two-state states, so like a spin up and down, these states are usually not very coherent, but this is a minor problem. The main problem is that the interaction with them is very, very, very small, right? So you have a very massive object, for instance, a large piece of diamond, and you have, let's say, one spin in it, right? So conceivably, you can make nice quantum experiments with this one spin, right? But how much K can you kind of create with that? And this is obviously very little, because it's a single spin and a very massive object. So this is a general problem of macroscopic things, to have good two-level systems to couple to, where you can really apply strong phase gradients forces to create large quantum states. Yeah, and the minor point maybe is that in two-path superposition states you have additional sensitivity to noise. Yeah, but the main point here is that it's very hard to create any strong interaction with two-level systems. For macroscopic systems. Okay, so on the other side, what is the right thing to do? The right thing to do is to use delocalized quantum states. So in the years, so a few years later, and then after those proposals, people proposed here in Kani and Krishnanda to basically to use macroscopic objects in Gaussian states and read them out with lasers. Okay, so this was proposed a little bit later. So why are delocalized systems a lot nicer? So for instance, one thing is that to create a beam splitter is now a very easy thing to do. You just measure the position very precisely, and that immediately gives you momentum uncertainty. So it's easy to scale up K, basically. Where on the other hand, with the two-path superposition states, this is kind of a tough ask. Okay, so what, if you put in experimental parameters, what are the rough parameters that you can have? So for instance, you can have 10 to the minus 8 kilograms, so a Planck mass separated by 100 micrometers. And if you then want the phase shift to be order 1, you need a K of 10 to the 16. Okay, so in this regime, the wave packet separation over the distance is much, much smaller than 1, right? So the wave packet separation will be on the order of nanometer or below a nanometer, and the distance is 100 micrometers. Okay, so you're very, very much in the small quantum state regime. Yeah, so the K 10 to the 16 I mentioned, so this means kind of if you use coherent laser beams, for instance, and you have a certain wavelength, then you need to have square root of n many photons to create this kind of beam splitter. So this is not yet a lot of optical power, but obviously if you want to go to K to 20 for LIGO mirrors, this is a lot of power that you need to have enough readout resolution. The other important number here is this quantum state expansion ratio. So this is necessarily to above 10 to the 5 for a 1 second time scale. It's closer to 10 to the 6 actually. So this is really the reason this is a problematic or a very tough experiment, this expansion ratio. And the sensitivity to noise is on the order of 10 to the minus 17 G. So compared to LIGO mirrors, obviously that's, well, still very good, especially at the time scale, but somewhat conceivable. But of course, this has never been done to this kind of small masses. Yes, so what about entanglement detection? So do you need to, is this kind of good enough to use Gaussian states for entanglement detection? And I would claim, yes, it is. Because if you look at the part of the interaction that creates the entanglement, it scales as the differential position squared. And there's a good coincidence, or that you have a nice inequality, which is the product of the uncertainties in the differential position and the common moment and the sum of the momenta, which has to be bigger than h bar squared for separable states. So if you let your system evolve long enough, then the uncertainty in the relative position between your two Gaussian states will go below h bar squared. So this is a very convenient and direct entanglement witness that you have for Gaussian states. Yeah, so I would claim this is the best way to do it, but it's still very, very hard. Okay. So now let's what can you do with this system, right? There have been a number of papers about different ways of interpreting this kind of experiments, but also to look at other measures for quantum nature of gravity. And the two things I would like to mention here is, on the one hand, we have minimal noise in non-quantized gravity by the authors up here. And basically they say it's very important to measure the noise in this kind of systems. Okay? So the noise is the excess noise gamma here, which is the sum of the noise on the two systems individually, excess noise. And this noise level, they then say we can compare that to the entanglement rate. And if we measure noise level below this entanglement rate, we can immediately claim that gravity is not quantum. So in this direction, it's very easy. If the noise so if there is noise on this order of on the entanglement rate, then it's obviously very hard to bound this excess noise number. Yeah, but even below the entanglement rate, you can rule out more and more parameter space of different classical models of gravity. Yeah, and what I'm trying to say here is that if you have an entanglement experiment which is supposed to measure entanglement, this is just the thing to also probe minimal noise. Right? So this is still the correct experiment to do, basically. You have two objects, you measure their position very precisely, and you look for noise, try to lower the noise, and also try to detect entanglement. Okay? So this kind of experiment is still the right thing to do. And so the other paper I have here is like testing quantum gravity without entanglement, which in the end, again, requires basically the same setup, just that you don't want your quantum states to expand too much, right? So the scaling is still very much the same scaling of the entangling rate, just now with a ground state size. Okay, so it's still basically the same experiment, just slightly or minor differences. On the other hand, an experiment which is quite orthogonal to this kind of entanglement experiments is experiments that try to detect gravitons. Okay, so this is obviously a very orthogonal, because here with the gravitons you have a graviton wave coming in and you have a single quantum system trying to detect it, which is very different from the interaction between two quantum systems. But obviously the problem is if the graviton waves that come in, or the fields, they're usually coherent states or supposedly coherent states. So the quantum term is a lot smaller than the leading order term, which is just given by the expectation value of the gravitational wave amplitude, right? So in order of quantumness, the leading term is of obviously less quantum than the entangling term. Okay. So, as I already mentioned a little bit about, I already talked a little bit about the problems with macroscopic bodies. First and foremost, thermal noise. Of course, there are other noise sources like seismic noise, which are also a problem, especially at long interaction times. Yeah, what I want to point out here is that if you look at LIGO mirrors at low frequencies, thermal noise is really very large. And since LIGO mirrors are fairly big, you need a very high resolution in principle to detect any kind of entanglement.
So there's really a big problem here at low frequencies with thermal noise, neglecting the seismic noise. Okay, so what can you do to combat thermal noise? The one solution is, which is especially necessary for small masses. So if you don't want to go in this very high resolution regime with large K, but just stay at lower K, basically, you want to use smaller masses. And one of the ways to avoid thermal noise or to reduce this is to use levitated systems, which can have very high Q for small masses, and which is impossible basically for suspended systems. So if you suspend a system with small mass, it's very tough to get competitive thermal noise values, basically. But the problem is there's still some residual thermal noise, and there's a strong interaction with the field, which is usually a problem if you want to detect something small, like the interaction from gravity. Do I already have 25 minutes? Oh. Well, okay, so basically my approach to this problem is not to use levitated systems, but to use freely falling systems. And the benefit, also the features of freely falling is that you have no thermal and seismic noise. And the only interactions you have are due to your readout interaction. Okay, so why free fall? So if you look at the atom experiments, you launch them in the fountain trajectory, and you have free fall time of a few seconds. And the important kind of what you learn from these experiments is that you can have very, very high control over their trajectory. So you can have always control to better than 50 micrometers over a 10-meter launch. And the other thing you learn is that the quantum states are very well preserved under free fall. So for instance, with atoms, you can have a quantum expansion ratio on the order of 10 to the 8, right? Which is quite a bit more than what we need for entanglement. But of course, this is with atoms, where everything is a little bit easier. So how do I want to do it? You take a macroscopic particle, a little mirror, you shoot laser at it to read out the position, and you let it delocalize during the drift time in free fall. And how is this going to be implemented? Hopefully soon. We use levitated superconductors for preparation. So we trap them in a trap, and we try to let them spin and then launch them on a fountain trajectory. And the idea is then, while on the fountain trajectory, we shoot laser at them and measure their position precisely, and eventually create quantum states with them and have two of these kind of mirrors close by to measure the gravitational interaction. Yes, I think I'm already over time, but that's it. Thank you.
Thank you very much, Peter, for the nice talk. Are there questions?
I mean, I'm sorry, I'm a theorist, and I'm going to ask the most annoying question that theorists ask experimentalists. So when do you expect this experiment to be completed?
When it's completed? Well, I don't know, 10 years plus.
10 years?
Plus, yeah.
Okay, so our next speaker will be Jan Mandrysch from a group of Miguel Navasque. And he will talk about how to measure quantum fields.
Hello, everybody. My task is now to switch gears again completely. So Markus addressed how diverse the research infrastructure here is, and now I go from experiment to back to theory again. So yes, let me start with our group. Let me start with saying, okay, present joint work with my group leader, Miguel Navasquez, and also upcoming work also together with Robin Simmons. I cannot progress. Now I can progress slides. Okay, here's Miguel, here am I. I represent the QFT branch, but there's also nice research in other directions. The metrology branch will be covered by Paolo later today, and we also have a new postdoc who will present works in the future, I suppose. Now, what is the QFT branch of our group? Maybe it's best described as the interface between quantum field theory and quantum information. And to do quantum information, that requires a selection of admissible states, measurements, and operations. You need to do. You need to know what you can do and what are allowed states that you can achieve. Now, while in conventional quantum information it is pretty clear, quantum field theory departs from the conventional setting. There are infinite dimensional Hilbert spaces around and further obstructions, which I partly cover in my talk. Especially the so-called Sawkins paradox that dates back to the 90s, which points out a particular issue with relativistic causality. Now, this talk will focus on characterizing the admissible measurements and operations. I leave out the states since there's already quite a bit known, and it's more than about measurements and operations. Okay, to start with, I have some motivational slides. Now, what we all know, how experiments are performed in to test QFT is in particle colliders. We shoot particles at each other, there's a zoo of particles coming out, and it's a quite uncontrolled process. And also in theory, we just basically compute only transition amplitudes, meaning from the in states, we compute probabilities that we get some out states that are then detected in the collision chamber. Now, as a foundational-minded person, we would like to know a bit more about QFT, especially how it locally resolves. So we should zoom in, and we should zoom in further, and somewhere there, our QFT that we are interested in should be visible. Of course, not in this picture. Now, starting with that, let's do more theory diagrams and make a supposed Gedanken experiment in order to classify what types of correlations we would like to, we think can happen in QFT. In particular, we take a bipartite setup that is well known as a Bell scenario, where we prepare a common state and send some parts of this state to two parties, usually known as Alice and Bob. And they both then perform measurements on these partial states and can choose different settings that are labeled here by J and K. And if both of them have performed a measurement, they should have received an outcome, here noted as A, J, and BK. They can send their outcomes together to post processes, and at this point we can then compute or check the correlations between the outcomes that we found. And if we do this experiment many times, we get statistics on these correlations. And if the outcomes are, for instance, just binary, then we can form a certain correlation variable and know by the so-called Bell's inequality that any local hidden variable theory will have p less or equal than 2. So to say, a classical theory will not exceed this bound. So in another sense, it's a test for quantumness if we exceed 2. But we can characterize further what happens above p equals 2. For instance, there is the so-called Siereltsens bound, which tells us that in any quantum theory, and it usually is supposed to include quantum field theory, we find a value that is bounded by 2 square root 2. There are two different paradigms. If we rely here in this bipartition on the tensor product structure or only on commutativity, that give us two slightly different sets. I will depict a picture in a moment. But there's another important bound, namely if we require no signaling, namely that we can reduce that the marginals of this correlation set that we don't have communication from one party to the other in between the experiment. This bounds the correlation by 4, so it's called then no signaling. And what is important is that while some slight exceedings of 2 square root 2 are thought to be maybe possible, as soon as we exceed it by a bit higher numbers and go towards 4, some foundational principles are violated, so that we don't expect our set of physically obtainable correlations to exceed much of 2 square root 2. And a picture of this we see here. So there are these are all convex sets. These correlations that we can achieve. The no signaling piece, smaller equal 4, is in blue, and then the Zirelson's bound 2 square root 2 as these two sets, quantum tensors and quantum commutative, and these should be almost close to what we can achieve in physically realistic setups. And what is an old problem in quantum non-locality is that these we would like to classify these sets very precisely, but if you take want to approximate them in certain ways, namely the inner set from the outside and the outer set from the inside, that's actually an undecidable problem. So that's an infamous result in this field. Now, having said this, it would be nice, of course, to understand what happens to this whole picture in quantum field theory, and there are further questions that I motivate on the next slide. Okay, this is the undecidability. I already mentioned that to do these Bell tests, we need statistics, so we need to repeat these experiments in space-time. So we need actually more knowledge on what is admissible in QFT to really make statements about these experiments. So for instance, we need to perform measurements, so we need to know what measurements are admissible. We need to perform several subsequent experiments, so we need, after these measurements were taken, need to update the state to perform the next measurement, the next experiment. And last but not least, it is also important where and when to update the state. So if we have performed our measurement here, at which point are we allowed to do the next one, for instance? Okay, and with all this, these are all questions in theory that we need to really describe such situations. And this motivates then the piece of research that I will give you now. Let me just check. Okay, time is good. Maybe I should slow down a bit. I think it was too fast, shooting everything at you. Now let me calm down a bit and progress what are admissible operations. Now, in QFT, there's some things are known since long times. Namely, if you perform measurements in causally separated regions, meaning there's no light ray that is allowed to cross from one region to another one, then the observables that are located in such regions should commute. This is known as microcausality. So if Alice has here observables or measurements localized in this region, and Bob takes it in this region, then since these regions are space-like separated, no communication can be sent, and in particular, we expect that these observables commute. Now, what was found in the 90s by Sorkin is that this is like taking the elements, the observables from these two algebras to also define your operations that you can perform, for instance, the measurements, will or could, in principle, lead to subliminal signaling, which we, of course, don't want in our theory. because we know it should not happen in real. And this problem arises when you put somebody in the middle. Now, if you put Charlie in the middle of this setup, he has overlap with Alice and with Bob, so there can be light rays sent. And if you allow Charlie to do arbitrary operations here, then it could be that Alice communicates to Bob. So it means that we need to restrict the set of operations that Charlie can perform. If Charlie performs only physical operations, then Bob should not be influenced by Alice. So the question is now how to characterize the physical operations, and this leads back also to the image I showed you before, to really narrow down where the physical operations lie. Okay, there are two main approaches. Top-down approach, invoking necessary conditions to characterize the physical set. So from the outside, we can, and there's a so-called path support non-increasing property written down by Jupp a few years ago. That's basically writing down a condition to avoid Sorkin's paradox. And if you avoid Sorkin's paradox, you know already that there's no superluminary signaling. So maybe this is all of these operations are already physical. On the other side, you can also do a bottom-up approach. You can start building up on the knowledge we have already, what in QFT you can do and cannot do. For instance, if you speak about Lagrangian theory, you know that usually only local Lagrangians lead to good interactions and that comply with causality. And there's a notable achievement a few years ago by Fuster and Perche, which formulated a framework which also allows you to define a reasonable class of operations you can perform on a QFT that complies with causality. Now, expectation for many researchers in the field were that maybe these sets are already almost closing, so that we have almost characterized maybe what is physically possible. But before addressing this issue, I would like to go into a bit more detail what this Fuster-Perche proposal is about. This framework originally mostly motivated to write down a measurement theory that complies with relativistic covariance, complies also with relativistic causality, and allows you to operationally write down the operations you can perform in a QFT. Notably, there's this star that marks that they have recently received the Ehrenfest Best Paper Award, which is also granted by the IQOQI Institute. Notes are that So this work was recognized in the foundations community quite a bit. And what is this framework about? Well, we have it's based on the idea of von Neumann. It comes from the 50s. That to classify what measurements you can do in a target theory, you can say, okay, it's what you can do is you couple a probe theory to that target theory, namely something that you know that you have under good control, that you now know how to measure it with, and if you form a certain protocol, then via the interactions that the target and the probe have, you can extract sufficient information to induce a measurement on the target theory. I mean, if we want to measure the electromagnetic field, what we do is we have some sensor that is sensible to this electromagnetic field. We couple it for a while to the field and then read off some value. And it's more that we know what the detector does instead of knowing what the target or electromagnetic field does. I mean, at least back in the times when we didn't understand electromagnetism. Okay, the protocol then summarizes as such. We prepare the probe in some selected state. We couple it locally to the target theory, and then we measure the probe and discard the probe afterwards. And in more quantum information style, we could note down this procedure as such. We start with the states of target and probe. We couple, we measure the probe, and effectively what we have done is we have measured a fictitious target observable. Problem of this, and as a result that this, the operations induced in such a way comply with relativistic causality. And what was an issue at the time, and is still also partly open, is that the way to define the target observables is quite implicit. We need to know the probe observable, the probe state, the probe interaction, and it's then indirect how this target observables look like, this TP sigma theta. And what we contributed to this is that we have a result that Gaussian field measurements can be represented in such a way, so they're implementable in this framework. And in the upcoming work, we will also address arbitrary non-demolition measurements of the field, basically showing that most measurements you would like to define can be implemented in the framework. So far, so good. This framework has some notion of completeness already. I can briefly give you a glance on the scheme, but just to show that we have done something, I will not go into the details. That would exceed the talk's time. And last but not least, I connect back to the beginning of the talk, the non-local correlations. There was this set, and since it's upcoming work, I will not go into the very details, but maybe you can already guess that we have found a way to also transport this picture in the QFT setting. So stay tuned for these upcoming results. With this, I thank you and for your attention, and I'm happy to take questions.
Thank you very much, Jan.
I had some take-home messages that I forgot, but I will just display it. Sorry.
Questions? Are there online questions?
Can I then just maybe briefly state one thing? So we had a beautiful workshop in the beginning of this week, and there will be nice events following up by the so-called RQI cost action, and this interface with QFT and quantum information is located in working group 1. So if you are interested in the general field, this cost network will provide a nice, there you on the webpage, and in general you will find all kinds of information you would like to see more research in that direction or to join the effort. That's
Thank you. Riccardo, please. Okay, our next speaker is Riccardo Falcone from Brukner's group.
I am very sorry.
He's a postdoc in Caslav's group.
Can you help me, please? Okay, thank you. Okay, hello to everyone. Thank you for allowing me to talk about this work. So just to give you a little bit of a context, let's say in laboratory experiments, especially in particle detection experiments, we usually consider, we naively assume that detectors act in an ideal way, in the sense that they never click in a vacuum, and they always click in the presence of a single particle that is ideally localized in the detector. In general, we can represent this sort of ideal measurement by using a localized POVM that gives you a yes or no sharp answer to the question, is there an excitation in this direction? So it has a 0 probability of clicking in the vacuum and a probability 1 to click for a particular state psi.
However, as one of the results of local quantum field theory, we know that this idealized regime is basically impossible. There is a no-go theorem that tells you that it's impossible to have a local POVM, in this case effect because you have a dichotomic result, that can give you a sharp yes or no answer to the question, is there a particle in this region? In particular, these two assumptions, they are incompatible. So what we did in this work is to try to relax one of these hypotheses. Of course, we didn't want to relax the first hypothesis. We assume that we always use like detectors that are localized in space. They act in a specific interval of time. So we relaxed the second hypothesis, and we talk about these quasi-ideal detectors that almost never clicks in the vacuum and almost always click in the presence of a particular state. Of course, the no-go theorem still applies. So we have a sort of trade-off between these two properties. In particular, if a detector is very good at satisfying one of these properties, then of course it must be very bad at satisfying the other property and the other way around. So we know there is this trade-off, but we don't know how to quantify. Like, it would be nice to have a certain inequality that gives you an upper bound for the p-click, which is the probability of clicking in the presence of a state psi, given the p-dark, so the dark count probability, the probability of clicking in the vacuum. And we would expect something like this, like if the probability of clicking in the vacuum is 0, then the probability of clicking in the state psi is also 0, because of the no-go theorem as before. But again, up to now, we don't know how to construct like an explicit inequality that gives you this constraint. And that's what we did basically in our work. So to give you, like the framework, of course, will be algebraic quantum field theory. You don't have to know nothing about algebraic quantum field theory. Just the fact that we talk about local algebras that can be, I don't know, generated by smeared fields, whatever. And this is the assumption we make. We assume that this POVM is an element of the local algebra. We don't make further assumptions. In particular, we don't give any, like, we have no assumptions about the particular physical mechanism of the detector. It can be, again, one of, like Jan was talking about, one of these measurements that can be actually realized in QFT. But this is the only assumption that we consider, basically. Then we use the, well, you maybe will know, the Ricci-Leader theorem, and we apply to the causal complement of the detector region. So we know that because of, as a result of this theorem guarantees the existence of a class of operators that are localized, in this case in the causal complement of the detector region, that by acting on the vacuum state, they're able to approximate the state psi with the arbitrary good precision. So now we have these two objects, the family A zeta and this error function. And by manipulating a little bit these objects, by doing some triangle inequality and stuff like that, this is the inequality that you get. So we finally got an inequality that gives you an upper bound on the probability of clicking given the p-dark probabilities. Now, I cheated a little bit because, unfortunately, the Ricci-Leader theorem only guarantees the existence of this family, but it does not tell you how to actually construct this family of operators. So we don't have an actual explicit expression for the inequality. However, in the particular case of coherent states, so if psi is a coherent state, we've been able to derive this object, so the Ricci-Leader approximation for these coherent states. So we have an explicit expression for the inequality that I showed before, but just for this particular case. But this is still nice because coherent states, they are commonly used in experiments, so this is still okay. And in fact, we try to apply this result on a very specific experimental scenario of a photodetector, photodetection scenario, where the detector region is represented by this prismatic shape, and the coherent state is a single mode coherent state with an amplitude, momentum, and coherence volume. And those are the results. So you can see here it's the upper bound of the p-click as a function of the p-dark, so the dark count probabilities. You can immediately see that regardless of the parameters that you fix, you will always see an upper bound that goes to 0 as p-dark goes to 0, which is what we expected. And also, you can see how these figures, they increase, so they go close to 1 or even over 1 by increasing this parameter n, which is the number of photons seen by the detector. A way to see this is the bigger the size of the detector, the more ideal the detector is. And this is exactly what you expect, because now we don't have a local measurement anymore, we have global measurement, so this is okay with the results. So these are the takeaways. The motivation, the initial motivation is that the locality forbids a perfectly vacuum silent, yet still responsive find detector. So we have a trade-off. We quantified this trade-off. And in principle, this inequality can be, hopefully, tested or verified in experiments. Of course, if we see a violation of the inequality, there must be something wrong with the theory. For example, the assumption that the measurement can be performed in terms of elements of local algebras, it can be incorrect and stuff like that. Of course, we don't believe in that, but never say never. Okay. Thank you.
Thank you very much, Riccardo. Are there any questions?
Oh, no.
Yes, Schubs.
Yeah, thank you. That was very interesting. Can you go back to the previous slide and explain again? Maybe you said, but it was a bit fast.
Yeah.
How can P be bigger than 1?
P bigger, this is not P, this is P max click. It's the upper bound. P greater than 1 means the bound is useless. The inequality gives you no prediction.
Okay, I see. And so, can you again comment on these curves?
Yeah. Okay, I would say the most interesting one is the one that I talked about, which is about the when you compare, for example, the blue line with the orange line, you would see that the orange one is more ideal than the blue one, because it becomes larger and it can go even beyond 1. And this happens when you increase the size of the detector, or if you also increase the amplitude of your coherent state. So the more photons it sees, the more ideal is the measurement, and the more useless is the inequality, basically. So, of course, if you want to test it, you have to go to the regime where it's less ideal.
Okay. Oh, more questions?
Could you explain the theta phi of the
Theta phi, it's a total accumulated phase. So K0 is the momentum, and L would be like the depth of the detector.
Is it a time resolution or is it?
Okay, tau is the time, and L is the length. Because you have to combine also like the possibility of, for long time of interaction, it would be basically the same as increasing the detector. And here, here also you can think about counting photons, I guess, I don't know, because the higher the frequency of the
what's the large L and the big L?
Okay, the small L is the depth of the detector, and large L is the length of the detector. The detector is, sorry, I give you a, yeah, this one.
Sounds like a fun experiment.
Yeah, we are thinking of that, yeah.
Okay, good. Let's thank Riccardo again, and Paolo, please.
Se non riusciamo. Anche soffro un po' di Parkinson, queste situazioni. Ok, aspetta. Oh, scusami.
Okay, our next speaker is Paolo Abiuso. We'll talk about the Planckian time of thermalization.
Okay. So, first of all, thank you to all the organizers. It's been a lovely day. And so we go for yet another change of topic. This will be probably the least relativistic talk of the day. And also for gravity people, I should say, first of all, that this Planckian time is not the Planck time related to gravity. It's a different Planckian time. So I will hopefully explain it. So yeah, let's start with it. Let's see if this works.
Yes, okay. So I will talk a bit about thermodynamics in the style of quantum info. So in the style of quantum info means like we are used to think of operational tasks that a user can perform, some useful tasks. And in particular, when combining this with thermodynamics, I will focus mainly on two operational questions, which are, first of all, how precisely can I measure parameters that are encoded in thermal states? So this is really a question of metrology. And second question is, what is the minimum time required to thermalize a quantum system? Okay, so these are, you can imagine them like as tasks assigned to someone. And in principle, these two questions, they seem very much unrelated, but I hope also to convince you that they are actually very much related by the end of the talk. And for the majority of the talk, I will only talk about the second one, okay? So what is the minimum time to thermalize a quantum system? Now, if you take quantum mechanics is a theory of physics that is governed by a fundamental constant, which is the, which is h, the Planck constant. And at the same time, if you ever did anything in thermodynamics, you will know that there is another constant hanging around, which is the Boltzmann constant, which assigns to any temperature a scale of energy, right? So if you ever encounter a problem of quantum thermodynamics, like a physical problem, that involves both quantum effects and statistical effects, you will most likely end up looking also at this quantity here, because quantum mechanics and thermodynamics assign in a very natural way to any temperature a time scale of this form, okay? And this we will call for during this talk the Planckian time scale of thermodynamics, okay? So it turns out that this appears in many contexts, and then for the first time, I believe like around 20 years ago, in this paper by Zanen, I think he was the first one kind of noticing that in certain superconductors, the charges of these superconductors above critical temperature, they seem to scatter extremely fast, as if they were scattering with a time scale comparable to this object here. So it was kind of claiming that they were scattering as fast as allowed by quantum mechanics in a way. And then actually this was even corroborated by experiments, by models of metals and insulators, showing that indeed this seems to be the case for large classes of systems. So then people started trying to understand why this happens, so trying to model, again, in condensed matter insulators, metals, and so on. And we have several classes of models that actually show how the dissipation of charges in this kind of system follows this time scale. Okay, so this appears in several works. At the same time, it also appears in the theory of quantum chaos. There was a conjecture by Maldacena and other people that this same time scale bounds the growth in time of these out-of-time order correlators. And also in this setting, there have been several works studying this. So over time, kind of an informal conjecture arose in different communities, and this can be seen also in some recent work saying, it's long been believed that dissipative timescale obey some kind of Planckian bound. There is also kind of a review of this dissipative bounds in metals, where this is discussed. So it is believed that this timescale should mean something about the minimum time of dissipation, okay? So what we did in this work was essentially proving this, okay? So it was essentially formally stating this idea of minimum time scale of thermalization or dissipation, and then proving it formally in a fully model-independent way. Okay, so how does the idea work? Well, the operational idea
is relatively simple. So we want to study thermalization as an operational task. Well, let's assume we have some system, the machine M, that is supposed to thermalize my system. So what does it mean? This means that I will fix the temperature, the target temperature that I want to achieve, and then I will put inside the machine, I will put a system that is out of equilibrium with some Hamiltonian. I will put it inside the machine at time 0. Then after some time, the time passes, and after some time, I take it out of the machine, of my microwave, and I want it to be the thermal state at the given temperature that I was willing to have. Okay, so this means that the state of the system should be close to the thermal state, so the Gibbs ensemble. Okay, so this is very general. It includes like standard thermal baths, local or global thermal baths, but also you can imagine that this is just a subsystem of a larger system that is thermalizing or whatever. Really, I just want anything that is engineered to result in a thermal state at the end on the local system. Okay, so this is a bit the idea in pictures. The idea in formulas is, well, number one, we require quantum mechanics to be valid, which means that, okay, the evolution is I take my system, I put it next to the machine, and then I let them evolve according to Hamiltonian quantum mechanics. That involves the local Hamiltonian of the system, some interaction, and the Hamiltonian of the machine. We do not make any assumption on the initial states of the machine, of the system, and also of the local, the structure of the machine that is thermalizing. The only thing that is fixed here is the local Hamiltonian of the system, because it's the one that defines the thermal state. So in the end, I want to reach the thermal state defined with this Hamiltonian. So this is, as far as one can say, I just require quantum mechanics, say standard non-relativistic quantum mechanics in the most general sense, without making any assumption on the state and Hamiltonian. And second, we require thermalization. Requiring thermalization means that after some time tau, the state of the system, so the state that is output on the system after interaction, will be close according to some distance epsilon close to the thermal state. Okay? And I require this to be valid for some region of Hamiltonians. Okay? This should happen not only for one Hamiltonian, because otherwise I could just prefer the target thermal state. If I want to talk about a meaningful thermalization, I want it to happen for more than one choice of the Hamiltonian of the system. So once again, this is just the thermal state. And for simplicity here, I consider the region of Hamiltonians to be a ball, but it doesn't need to be. So I would say this is a formal notion of thermalization in a weak sense. I just want the state somehow to be close to the thermal state. This is approximate. It just needs to be, I write it as a condition for a ball of Hamiltonians, but it doesn't need to be a ball. It can be any region. Some other details that I don't have the time to talk about, but we'd also take into account time resolution, partial informations, like what happens if I cannot make full tomography of the output, or even initial correlations here. So this is fairly general. And I would also say that it's kind of minimal assumptions that you have to make in order to get any result out of this. Okay, so I will just keep these things that I just described here. What we are able to prove under these two assumptions is that then whatever machine satisfying this, the time of the operational time of the machine needs to satisfy an inequality of this form. Okay? And in this inequality, you see the Planckian time of thermalization, and an adimensional number, chi, here, that has more or less ugly definition that involves the distance that we chose, which is the Bures angle. These are, again, the thermal state in the center of the ball, and this is the thermal state close to the center of the ball. This is the error here, and this is the spectral semi-norm of the variation of the Hamiltonian. The details don't really matter here. The crucial thing are the properties of this adimensional number. So this adimensional number, if you look at it, you will find that it's a finite number and it's smaller than 1/2 in general. And it depends clearly on the
generality, so on the set of Hamiltonians that I want to thermalize, and also on the precision of the thermalization, so it contains the error here. However, the most important thing that we are able to prove about this number is that not only this number is bounded by 0.5, but it's actually very close to 1/2 almost always. By almost always, I mean anytime the thermal state that I'm looking at is not a pure state, so which means anytime the thermal state that I'm looking at is not a ground state. Okay? So whenever I'm looking at the thermalization of states that are not pure, that are not at 0 temperature, essentially, then this number can be, it's very close to 1/2. Okay? Which means then when you go to very low temperature, then it goes to 0, this number, but it goes to 0 in this fashion where delta here is the spectral gap of your system. So putting these properties inside this inequality can be summarized as, for thermal states that have a temperature high enough to not be a pure state, so that are mixed enough, like thermal states the way we used to think of them, the inequality reads tau larger than the Planckian time divided by 2. So this is a formal proof of somehow what people used to think. And then when you look only at ground states, so you go to gap states and you put the temperature low enough, then the same inequality transitions to an inequality that reminds of the adiabatic theorem, okay? Which kind of makes sense. If you are only required to thermalize, to prepare ground states, then you are bounded by the adiabatic time scale. Okay, so I have no idea how I'm doing with time. I have 3 minutes left. Okay, then I will completely go over I will not, unfortunately, talk about the proof. This is a plot showing what I was saying in words, which is if you require an error that is small enough, then this number chi can be lower bounded by numbers that are very close to 1/2. So this is just to say with a picture that I was not lying. And then I also want to give you an intuition of why. So I didn't give you the proof, but I want to give you an intuition of why this happens. So the machine essentially only has to comply with quantum mechanics. So the only thing that it has to do, it needs to distinguish different possible inputs of the local Hamiltonian of the system. And it should output the thermal states accordingly. So if I give you Hamiltonian H1, you should give me output thermal state 1. And if I give you Hamiltonian 2, you should give me the thermal state 2, right? So overall, it's a unitary quantum dynamics. So the overall dynamics of both the machine and the system is governed by the Hamiltonian, and in particular is also governed by the local Hamiltonian. And if I change it, the output should also change. I want the thermal state to be different, but this needs a minimum time in quantum mechanics. And this we know from the theory. So in particular, if you imagine the system to be exactly the thermal state after time tau, you can imagine that by varying Hs, the variation of the output of the system should be the variation of the thermal state. And this one is order delta H time divided by H bar, and this one is order beta delta H. So you can get an idea of why, if you want to compare these two things, then the time should be comparable to beta H bar. Okay? This is just a hand-wavy argument. I cannot show you the full proof now. And at the same time, you get a feeling of why the machine, what is trying to do, the machine is actually trying to estimate Hs. The machine is trying to distinguish possible values that the local Hamiltonian of the system has. So this is why this is connected to metrology. And again, going very quickly, this is actually a problem that we solved previously, which is exactly the problem of what is the optimal sensitivity that a variation of Hamiltonian can induce in a thermal state. This is a very well-known problem in metrology that was solved and kind of, it's known to be bounded by this expression for Hamiltonians that are encoded in the unitary evolution of the system. If you encode any parameter inside an Hamiltonian of a system that thermalizes, we find an optimal sensitivity that looks like this, where this is the spectral norm of the derivative of the Hamiltonian. And then we solve essentially the problem of metrology at, say, at thermal equilibrium.
Okay, and if you just compare these bounds among them, so the problem of metrology on a ground state, a thermal equilibrium, or on a unitarily evolving system, you can see that by simply comparing them, you can get an idea of why this time here needs to be larger than, say, beta h or beta divided by, or beta delta. This is, again, another hand-wavy argument. So, okay, just to summarize, this Planckian timescale, it appears very naturally if you do anything in quantum thermodynamics, and it was supposed to represent a minimum timescale for thermalization. What we did was proving exactly this for systems that are mixed enough. Otherwise, it gets substituted by the adiabatic timescale. The techniques we used are based on Fisher geometry and metrology, and actually the same techniques can be used to solve the problem of metrology on ground states and thermal states. So you can find more details. Do I have like 1 minute more?
Okay. Yeah.
I just want to go into full speculations. I will skip the first speculations. I just want to talk about the second speculations, which are a bit more relativistic. So there is a conjecture by people like Susskind saying that black holes are the fastest scramblers of information in nature, and they satisfy a bound of this form. So the time that they take to scramble information is essentially the Planckian time times log n. So this looks very similar to what I presented you so far, except for the log n, because what we are able to prove is this thing without the log n, where n is the size of the system. So my question is now, for the people that are interested, is it possible that maybe we are able to understand this conjecture in light of what we were able to prove? Can we extend this to relativistic settings? So I think there are some things that we can get out of this. For example, when looking at time at the question of what is the minimum time of doing something, there is a very easy way of translating this to between different different reference frames, right? The minimum time required to do something should transform very easily under Lorentz transformation, for example. So maybe we can understand a bit how thermodynamics works also under relativistic transformations, let's say. So after this, I just want to thank the co-authors, Martí Perarnau, Pavel Sekatsky, John Calzamilla, and Alberto Rolandi, and these are the references. Thank you.
Thank you, Paolo. Questions?
Can we see the sketch of the proof a little bit?
Yeah. So the proof is a triangular inequality. I can try. Yes. So the idea is the following. Let's say you want to prepare these two thermal states that depend on the Hamiltonian. So I want to prepare thermal state 1 with Hamiltonian 1 and thermal state 2 with Hamiltonian 2. These are the target that you want to prepare. Now, if you want to do this up to an error epsilon, it means that the true output of the dynamics will be in this ball for case 2 and in this ball for case 1, okay? Which means that the distance between these two states, the actual states that you're preparing, should be larger than something via a triangular inequality. It should be larger than the actual distance that you were targeting minus the error, okay? Now, once you go into the unitary picture, so this distance of these guys can be bounded by some, I can give you more details, but some kind of speed limits, let's say. Not exactly speed limits, but some kind of. That that are upper bounded by the difference of the spectral norm of the difference between the Hamiltonians. So once you get this inequality here, then you see that you have a lower bound for tau, and then you bring it on the other side, and then you have a lower bound for tau, and you can get exactly this Planckian time and a number that then you can try to maximize over the region of interest.
Yeah, it seems now that the proof is complete, that the bound you had in the previous slide was introducing a maximum of a kappa, etc.
Yeah, exactly. So this would be the proof for only two Hamiltonians. So suppose the machine is only required to thermalize two Hamiltonians, there is already a lower bound. Okay. Then if you have more, then the lower bound goes up. Yep.
Let's thank Paolo again. Our next speaker. Our next speaker is Phil from IQOQI Innsbruck.
If you don't manage, I can help you answer it. Maybe. Almost hit it. I can try to help you. You're going to put it from the other side. Technology. Oh, wow. Amazing. Okay.
You can just.
Is this working? Okay.
Okay. Hi, I'm Phil. Just a slight correction. I'm not from IQOQI Innsbruck, just the University of Innsbruck, but they're across the hall, so basically it's the same, I guess. Yeah, so I'm going to be talking today about a work that I recently published, and it's going to be more of the Unruhigkeit setting, so it's going to be completely different from the previous talk and the talk before that. Okay, so I'll just jump right into it. So it's going to be related to, if you've ever heard of entanglement harvesting, it's going to be sort of in this direction. But I'm going to be talking about something called contextuality, which I'll try to briefly explain. No, that's the wrong way. Okay, so the motivating question was, we all love entanglement, and there's a huge body of research on this. And I wanted to ask, what else is there in quantum fields? So maybe there's coherence, there's mutual information, but there's one thing that I kind of had in mind in particular, and I was thinking of contextuality. This is one of my favorite topics. So this is another resource that we can kind of pull out from the field, and this is a resource which I kind of consider to be closer to what's the difference between classical and what's the difference in quantum. So then I set it out to try and show that we have our UDW system, we make it non-contextual, and then we see after the interaction with the vacuum, can we get contextuality? And so contextuality, kind of briefly, or perhaps before I say this, I had a secondary motivation, which was also to show can we have this resource with, let's say, entanglement as well? So that'll be a side question that I'll also talk about. But contextuality, it's a complicated topic, but I'll just say briefly that, let's say you have some local data, like probability distributions from doing some experiments, and you want to ask the question, do all of these come from one big distribution, one global distribution? And contextuality is essentially saying, if there is contextuality in the system, basically the answer to that is no, you can't do that. You can't think of there being this big global thing. So just an example, this is also the scenario considered in the paper, so called the pentagram scenario. So these are the observables, and this is the compatibility relations between them. So when there's a edge between these nodes, it's that they commute. So this defines a context. And this is a probability table for this. So these are each of the contexts. These are not real probabilities that I got from anything, just made them up. And so how this goes is, so you have this proxy that you're going to gauge the contextuality. So it's sort of this contextuality inequality. And how it goes is you say that because the -1 outcomes are all zeros, then the graph associated to just getting the -1 outcome should have max independence number of 2. So the classical bound should be 2. And then if you want to take the expected value of the -1 outcome with respect to this hypothetical global distribution, you sum these, or these, they're the same. You sum them and then you find, it's greater than 2. And quantum mechanics sort of generically predicts that this happens for, in this case, not every state, but there exists inequalities where every state is like this. So that's basic on contextuality. So this is going to be a perturbative approach, so there's not really going to be that much contextuality that we get out of the state. So with that in mind, I was thinking about, let's use a continuous measure. And there exists a continuous measure called the contextual fraction. So the thing I had before was called an empirical model, and it's just a probability table. And basically what you can do with any empirical model is you can kind of break it up into this contextual part and the non-contextual part. And this is the contextual fraction. And the contextual fraction is just saying how much of this model is explainable with a contextual model, and then how much of it is explainable with a non-contextual model. And so that's how I'm going to measure the contextuality that's generated from this interaction. You can read more about it in this paper here. Okay, so the Unruh-David, just going to go through this briefly. We have our quantum system embedded in a space-time, and it moves along some world line, Z. And its free evolution is just this Hamiltonian here. And this is the energy gap. And at some point, it interacts with this background quantum field. And the interaction is smeared out over this region according to this space-time smearing function. And this determines, so this lambda is determining how strongly it interacts with the field. And so that's going to be the basic model, how I'm going to do this. So this is just the difference between the initial and final. The initial, in this work I set it up to be 0, so essentially it's just this, but if there was any, we don't want to consider that to be in our final assessment. So just the protocol essentially works like pick the initial state to be non-contextual, and this is always defined relative to the scenario that you pick. So you have to set up the set of observables you want to measure. And in the perturbative approach, it's a bit tricky, so you kind of have to tune it a little bit so that you get this nice violation. So there's a little bit more going on than just that. And then you couple to the field. You trace out the field degrees of freedom, and then you evaluate this delta CF. It's a very simple protocol. Okay, so before I go to the results, just as is the case in entanglement harvesting, not everything is due to the field interaction. There's some classical signaling through the field-mediated signaling through this symmetric propagator, and we have this Hadamard function which measures the state dependence, which is just the anti-commutator of the field. The smeared one, sorry. And so I created this measure which is just saying the state-dependent part should dominate over the classical field-mediated part, and the contextual fraction should be greater than 0. And so this is what I'm going to call genuine harvesting. And so with all those things, I'm going to say, can we call it harvesting? I want to say yes, because one, due to this, the multiple works by Summers and Werner, the vacuum state is very non-classical, has a lot of contextuality or Bell-known locality. They're the same, but so we have existing contextuality. We have also a resource theory for contextuality to identify free operations. So we kind of take this and apply it to multiple levels to say, oh, we got contextuality. Oh, was it because of one of these free operations? Yes, then we just throw that out and we try again. And then I want to say that because the state-dependent part is going to dominate, I'm going to take these three things together to say that it was actually because of the field state that we got this result. This is not 100% rigorous. That's one thing that I want to do in the future, but that's how I'm going to argue that you can call it harvesting. Okay, so I chose a single qubit as the first thing, and that's just because there's no entanglement that's possible with this, with just a single qubit. So we want to see this bare non-classicality from just a single system. And so here we have the state that the final state that I had in the work, and just to point out these two terms, so these kind of motivated this genuine harvesting condition. These are the terms that really supply that take the vacuum fluctuations, which is sort of the entanglement between the field and the system, and create the contextuality in the system. And then here, so these are just, this is a smaller spatial smearing, this is larger. The T's are the temporal interaction window. I'm almost done. And I just wanted to point out one thing, which is that we can have gapless harvesting. And gapless harvesting is not possible for entanglement, but it is for contextuality. And that was one thing that was a little bit surprising. And the rest of the figures kind of behave similarly to entanglement. Maybe in the interest of time, I skip through the other qubit qubit. Yeah, I'll just skip that. But yeah, anyways, thanks for your questions. Sorry, thank you for your attention, and I'll take questions.
Thank you very much, Phil. Questions?
So if I get a qubit and then I put it to interact with a classical field, right? Same as the interaction that you have with the quantum field is replaced by a classical field. And then I shoot a classical field state. Can I produce contextuality in your setup?
You mean like...
Can I produce the W11 and W2 or terms in these positions of the density matrix?
You mean like with a quantum control thing, or?
No, it's not even quantum controlled. It's literally the interaction you have, but replace that field by a classical field, and I tell you what's the profile of the field.
I would say no, because that's going to rely on the symmetric propagator terms being more dominant, and
it will be a different interaction if you haven't changed.
It will be a different interaction, that's true, but I will say that, so maybe yes, you could, but that's why I tried to make it this genuine argument, because I want to like throw those away, say that that's more to do with signaling than it is to do with the actual field state.
I mean, you have one detector, so there's no signaling between different detectors, right?
This is the detector signaling, I guess, to itself in a way.
Yeah, but I think that the argument would be more solid if you use if you compare that with a classical field interaction, and then saw whether a classical field could also produce this sort of contextuality.
Yeah, what I was mentioning as a sort of future work is I want to investigate the general conditions on transformations to see when I can just rule out this transformation as being responsible. So in particular, that would be a type of transformation that I want to study. So yes, it's a good question.
Thank you.
Okay, thank you very much. Now we close the last talk of the RQI Circuit Vienna. So Rick, would you like to?
Sure, I can just give some final words. So, well, thanks everyone for showing up and holding up until, well, what's now 6 p.m. at the RQI Circuits. So 7 hours of broadcast, lunch, coffee breaks, many, many talks. I think that we had a very good overview of the overall research being done in IQOQI and, well, overall in Austria with all the comments that Markus had and now with Phil's talk. So thank you so much for being a part of this. And I'd like to thank the organizers, Emil, Lin-Qing, Jan, Manuel, Bruna. Thank you so much for putting this together. Without you guys, it would not be possible to do anything like this, so please. And then just the final thing is that, well, RQI Circuit is happening every Friday until July 31st. So next week we'll be in León in Spain. It's basically this postdoc meeting that Jose Polo Gomez is organizing with young postdocs and late PhD students. There will be less talks, will be easier to follow in this sense and shorter. So feel free to tune in the YouTube channel. And then the last thing is, please don't forget to register at the ISRQI if you're interested in these things, if you're interested in the circuit or in this sort of research or in the community overall, and in the RQI North, which are our yearly conferences and events where everyone gets together. So yeah, thank you. Thank you so much, everyone.
Thank you, Rick.
Wait.